Good morning. Welcome back, everyone, to day 2 of our 2023 Alaska Sustainable Energy Conference virtual workshop series called Energy Storage Beyond Lithium Batteries, sponsored by the University of Alaska Fairbanks and the Alaska Center for Energy and Power, or ACEP. My name is Jeremy Vandermeer. I am a research assistant professor at the Alaska Center for Energy and Power at the University of Alaska Fairbanks. Thank you for joining us. I am calling today from beautiful sunny Fairbanks, which is on the University of Alaska Fairbanks campus and is located on the lower Tamna-Benny land. As we shared yesterday, this series of 3 virtual workshops is being held monthly as 2 half-day Zoom sessions free of charge leading up to the Alaska Sustainable Energy Conference happening in person on May 22nd to 25th at the Denina Center in Anchorage, Alaska. We kicked off with low carbon energy transitions, lesson learned from the global pathfinders in March, followed by carbon capture sequestration, the myth and reality in April. And we're wrapping up this series with our program here today. If you're interested in checking these out, recordings of each of the virtual workshops will be available on the Alaska Sustainable Energy Conference website at www.alaskasustainableenergy.com. In yesterday's workshop, we kicked off with 3 speakers who set the context by giving some higher level overviews of the need for energy storage, the types of energy storage that are available and being developed, and the evolving use cases for energy storage. These were all extremely useful and interesting talks, and if you did not get a chance to listen to them yesterday, I would highly recommend listening to the recording when it comes out. Following those overviews, we started looking at some individual technologies that fit into either mechanical, electrochemical, chemical, or thermal energy storage categories. Yesterday, we covered pumped hydropower, which is a form of mechanical storage, and distributed electric vehicle to grid storage, which is a special use case for an electrochemical storage. And these are both very useful talks full of Alaska-specific information, including a report from Argonne National Lab and NREL that will be released in the next several months on the potential for pumped hydro storage in Alaska, both on the rail belt and in remote communities, and an electric vehicle financial and emissions calculator by ACEP that is available for different communities in Alaska. I would highly recommend listening to those talks if you have not already. So looking forward to our time today. We can see our agenda up here on the screen. Today, we will have 3 panels. Each panel will have speakers representing different electrochemical, chemical, and thermal energy storage technologies. And I'm very excited by all the great speakers and moderators that we have today. And I think we're going to learn a lot. The technologies that will be presented today are by no means comprehensive. If you remember from yesterday, there was quite a few. But they do provide some really excellent examples of technologies that are available commercially today. Each presentation will be followed by a Q&A between our attendees and presenters, so be sure to enter your comments and questions in the chat. And so before we get started, we're just going to kick things off with something a little lighthearted to break the ice. So we're going to have a poll, and if you can either scan the QR code with your phone, or if you go to slido.com and you enter this number code that you see on the screen there, you can participate in the poll. And so and then the link to the poll is also posted in the chat. So if you go to the poll on the screen, the first question we want to ask today is, all right, so large-scale deployments of electric energy storage will play a critical role in Alaska's energy future. So this is a highly subjective question, and so we're accepting subjective answers. Do you strongly agree, somewhat agree, do you strongly disagree, somewhat disagree? So we are seeing mostly strongly agree and somewhat agree. All right, and we're seeing, so we're seeing about 85% strongly agree, 15% somewhat agree, Yeah, I think that's very reasonable. Interestingly, no one disagrees. So that's kind of interesting. All right, let us go to the next question. So did yesterday's talks change your opinion on the availability of cost competitive energy storage solutions over the next several years? So yesterday we got an overview of a lot of different energy storage technologies, and it was really interesting. So we're seeing some people, about 3/4. A lot of people are more optimistic. Some people, there's no change. Some people did not attend yesterday. No one is less optimistic. So all of our speakers were pretty rosy, it seems like, about the future. It seems like overall people are more optimistic. I know I definitely came away learning a lot from yesterday's talks about all the really amazing technologies that are being developed and that are actually some which are commercially available now and have some deployments that are coming out. So, all right, that's awesome. So a lot of people are 72% are more optimistic, 70% no change, and then there's a few people that did not attend yesterday. So welcome to today's workshop. And so thank you for participating in this morning's polls. Next, I just got a few housekeeping items that I have to go over. So please introduce yourself in the chat. Let us know your name and the organization that you're from. And today we have a little extra bonus challenge. If you have your favorite energy storage pun, you can also add that as well. That's courtesy of Dave Messier, who's one of our moderators today. And if you're experiencing, and during the workshop, all attendees will be muted. You may submit questions or comments by using the chat feature, and our moderators will read the questions to the presenters at the end of each session. If you experience any difficulties with audio or have trouble viewing the presentations, please chat to chat support for assistance, and you'll be able to find them with there'll be like a little blue option window on top of your chat box to choose who you're sending a message to. And the recording for this workshop will be available on the ASEC website at www.alaskasustainableenergy.com at a later date. So if you have to step away or want to rewatch or share our presentation, you will be able to do that. And so this brings us to today's first presentation, which is the electrochemical panel. As a reminder, during this session, questions can be submitted via the chat box and will be addressed during the Q&A immediately following this presentation. So please join me in welcoming our first moderator, Rob Royce, who is the Chief Innovation Officer at Launch Alaska. Rob manages Launch Alaska's team of subject matter experts in advising organizations on the development of strategic plans that harness Alaska's distinct mix of resources, markets, and opportunities, and successfully scale solutions that accelerate the resource revolution. Rob has spent the last 15 years nurturing the adoption of grid edge technologies in both islanded and grid-connected power systems throughout Alaska and the Caribbean, as well as the lower 48. Whether as an energy advocate, opportunistic river guide, or husband and father, Rob's passions motivate him to invest in a sustainable future as he explores the grid's edge in both work and play. And I've known Rob for quite a few years now, starting with his time at ABB, where he supported the battery installations going into Alaska at that time. And Rob continues to be both an energy storage subject matter expert and a real champion for energy solutions in Alaska. And today is actually Rob's birthday, and yet he still agreed to be with us today. So really, thank you, Rob, and we appreciate being here, and the floor is all yours.
Thanks so much, Jeremy, and good morning to everyone. As he mentioned, I'm Rob Royce, and I'm pleased to be moderating today's panel on electrochemical energy storage. As Jeremy mentioned, it is my birthday, so I'll start us out with the best birthday pun. What is the best battery for dessert? The answer would be lithium. So I'll be celebrating my birthday both on this panel as well as later today. Thanks so much. The poll responses were super interesting. Everyone seems to agree that energy storage will play a major role in Alaska's energy future. And overall, more people are optimistic on the commercial and competitive availability of systems today. Alaska has a rich history of innovation in energy storage. So rich, in fact, that storage systems have, in my opinion, become near standard for renewable integration in the smallest to the largest of power systems in the state. With the proliferation of storage in Alaska and the unbelievably rapid growth of storage around the world, it's easy to forget some of the early pioneers in Alaska's market. Most of our audience is likely familiar with Golden Valley Electric Association's battery energy storage system, commissioned in 2003. At the time, it was the world's most powerful battery until 2019 and is still operational today. But there was actually an older nickel-cadmium system in Alaska than Golden Valley. It was Alaska's first diesel-off operation, and it was a system commissioned in 2001 in Wales. This system proved that high-penetration renewable systems were possible, though it would be nearly a decade before another system achieved functional diesel-off operation. If you go back further, Metlakatla Power and Light installed the valve-regulated lead-acid battery in 1996 to stabilize their local power system. The system managed the peak demand of a local sawmill, and it allowed the utility to baseload their hydro resource. The system still operates today, though it is being replaced with a new lithium-ion system. Finally, and even further back, is another example of the modern application of energy storage I think is worth mentioning, albeit mechanical, not electrochemical. In the late 70s, Usabelli Coal Mine installed a 40-ton flywheel to manage their 6 megawatt peak and 2 megawatt regeneration swings from a massive drag line they used to remove overburden. The flywheel operated for decades and stabilized the local power grid that would otherwise see flickering lights every time the drag line moved. Building on that legacy, today I'm excited to be joined by storage experts that will share with us the evolution of battery chemistries, starting with the one we're most familiar with, the family of lithium-ion chemistries, as well as sodium sulfur and zinc bromine. They'll explore what makes each unique, the role these chemistries may play in the future, and the opportunities for Alaska to leverage their respective advantages. We'll take your questions in the chat as the panel proceeds, but we'll save them for our panelists following all three presentations. First, I'd like to introduce Lynn Trahey. Lynn will be presenting on lithium-ion batteries with a high-level overview of the current technologies and what is coming down the pipes for them in the near future. She is a materials scientist at the Joint Center for Energy Research's Battery Hub, where she leads internal and external research integration efforts. As staff scientist at Argonne National Laboratory since 2010, Lynn's research focuses on operando characterization of tailored materials and interfaces for advanced rechargeable batteries. Talking with Lynn before this panel, it's obvious she's interested in more than just battery chemistries, and she's passionate about training and developing the workforce in the United States and building local capacity by working with our communities, vocational schools, and universities. Lynn, take it away.
Thank you, Rob, and thank you to everyone here. Good morning, Alaska. I wish I could be there in person. So this is an electrochemistry panel. I'm brought on to talk about lithium-ion batteries. As Rob said, I'm part of JCESR, which is the Joint Center for Energy Storage Research. This is a program funded from the U.S. Department of Energy Office of Science, and we do not work on lithium-ion batteries. We particularly work on what's beyond lithium-ion batteries. But I do have a background in lithium-ion batteries working at Argonne National Laboratory, so that will be the focus of my talk today, and I really look forward to all of your questions. So I wanted to start by going backwards a little bit. This is about lithium-ion batteries and the changing energy storage landscape. So JCESR, the hub that I work in, started in 2012, and we framed ourselves to go beyond lithium-ion batteries. But what was happening in 2012? Well, lithium-ion batteries, of course, dominated personal electronics, and it was really one size fit all. Everything was as high energy dense as possible and affordable to be put into your hand. Looking at the grid, lithium-ion was a very small fraction of grid storage only 10 years ago. The most capacity-wise is pumped hydro, and that will remain the case for a while because of the size of those installations. But when you break down what wasn't pumped hydro, that was energy storage on the grid, batteries were even a smaller subset of that piece of the pie. Lithium-ion, sodium sulfur, and lead acid all made up something in the megawatt range of energy storage on the grid. This is just 10 years ago. Now, for a preview, here's a graph from Bloomberg. Energy storage just has to blow up on the grid. This is based on the global cumulative energy storage installations projected, which means that they are, breaking ground and absolutely going to happen between 2015 and 2030. And now we're in a gigawatt scale, and this graph excludes pumped hydro. So just the scale of expansion for energy storage on the grid is enormous, and this has led to a giant market. And I think we're all here today because we know that this has to happen, and it is happening. Something else has happened between the start of the program I work in and now, and that is that lithium-ion batteries awarded 3 people the Nobel Prize for their work in generating this technology. And it's really important to know that any sort of net zero conversations or just reducing greenhouse gas emissions, none of the projections and goals could even be possible without the invention of the lithium-ion battery. So it really enabled the world that we need to get to. And without it, I just can't imagine. So just for some background on the Nobel Prize, these 3 men, Stan Whittingham, John Goodenough, and Akira Yoshino, were awarded the prize. It all started with Stan Whittingham. The first lithium-ion battery that he invented when he was working for Exxon in the 70s was lithium metal and titanium disulfide. So he had the vision that lithium could intercalate into lithium disulfide at the cathode of this battery and then go back to the lithium metal. And it worked. The problem with this cell was that it was extremely flammable because lithium metal in this configuration would form dendrites and cause fires because of shorts. And they caused so many fires that they had to, you should read all about this on nobelprize.org. There's really good stories about the origin of all of this work. But safety, let's just say, was a giant concern. So the price of oil plummeted in the 1980s. So ExxonMobil stopped funding this type of work. But John Goodenough developed a different cathode for the battery. So he still used lithium metal, but instead of the titanium disulfide, which gave you a 2-volt battery, he expanded this to a 4-volt battery with the adoption of lithium cobalt oxide. This is a beautiful cathode material because it doesn't change really at all when lithium goes in and out. It stays topotactic. All of the elements inside barely shift in any way. So you have a lot of stability at 4 volts. So this gave you a lot of energy. However, the safety issue was not yet solved. This was not solved until we moved to petroleum coke in place of the lithium metal. And then we have the battery that we're all completely familiar with today that probably everyone has within 12 inches of their hands right now. So this is a carbon-based anode and a transition metal layered metal oxide type cathode. Now, where are these lithium-ion batteries used today? The graph on the bottom by Bloomberg shows 2011 to 2021 passenger electric vehicles, electric 2- and 3-wheelers, e-buses, commercial electric vehicles, stationary storage, and consumer electronics. The fraction of use by consumer electronics is pretty steady and will always be there. Stationary storage is the pink band, and that's growing and growing and growing. But really the big boom has been in passenger electric vehicles. I live in Silicon Valley, and you cannot throw a rock without hitting a Tesla. In 2012 is when the first Tesla, the major Tesla model came out. We're blanking on what that was, Model S maybe. And then now they're everywhere, and there's way more than the Tesla that started in 2012. So we've all seen that passenger electric vehicles, which rely heavily on lithium-ion batteries, are out there. What's interesting to me is that capacity-wise, lead acid is still one of the biggest amounts of capacity in cars, and only now are lithium-ion batteries providing more capacity to cars. We need the lead acid for starting an ignition. Okay. Where we are now is that the cost of lithium-ion battery is down about 1/5 of what it was in 2012. There's an incredibly high demand for cars and grid storage, but one size does not fit all. It's not a panacea for every application out there. They are fantastic for passenger cars and 4-hour grid storage. If you were here yesterday, you probably heard a lot about the 4-hour mark for lithium-ion batteries. At full power, they last about 4 hours based on how they are configured. They are not viable for heavy-duty transportation or multi-day grid storage, not affordably viable. They could do it if you could add more and more and more, but who can afford that? And they have a very expensive and earth-limited international supply chain. So we need many more options, and we need to put them in the right places. Let's look inside the black box of what a lithium-ion battery is, because this is an electrochemistry panel. In the super simplistic figure, you see current collectors, anode, cathode, lithium. Just know that in the actual cell, there's not a big flood of electrolyte inside. All of the electrolyte inside the blue area on this schematic is kind of penetrating a physical separator because the anode and cathode are squished together for space. All right, so the electrode materials, the anode and the cathode, they are what we reversibly store lithium. And what makes this battery so exceptional is that the anode and the cathode don't change much. You know, like I was saying before with the invention of LCO, it doesn't really move. It doesn't change size. It doesn't change shape. It doesn't change phase. And that stability is crucial. The negative electrode normally, state of the art, is graphitic carbon. In higher energy density applications, they are adding a little bit of silicon to these electrodes. Silicon by itself is problematic because if you only use silicon instead of carbon, it wants to expand dramatically and then contract and then expand. And expansion and contraction of an electrode, especially an anode, will lead to a lot of interfacial impedance issues. So a little bit of silicon is working, up to 10% or so, depending on who you talk to. But this is really just to get higher energy density in a battery, which is at the cost of lifetime. Now, the problem, if you are only considering grid applications, you do not need the silicon because it will, reduce your lifetime, and you may not need the increased energy density due to your site specifications. Now, the best anode would be lithium metal, but we know that that has a lot of safety challenges due to dendrite formation, and many researchers are working on making lithium metal work. And part of what's making that work will be solid electrodes, but this is just a topic of research and small scale adoption into the market. Now, the cathode is our positive electrode. This is usually a layered metal oxide. Oftentimes, you'll hear people talk about lithium-ion batteries based on what the cathode is. Like the chart on the bottom right by Battery University is the watt hours per kilogram of different cathode materials, which you can see there in orange. LTO, lithium titanate, can also be used as an anode because of its relatively low voltage. You can pair really any two things can make a battery as long as their voltages are different versus each other. So LTO versus NCA, which is nickel, cobalt, aluminum based layered metal oxide, that will give you a battery, which is actually a pretty decent cold temperature battery for Alaska because LTO has pretty good charging characteristics compared to graphite, but you will have a smaller voltage for your battery and need more of it if you need that amount of energy to be high. LFP is a very common cathode material people are talking about right now. That's lithium iron phosphate. Why that is popular, despite its lower energy, is that it has no cobalt or nickel in it. So it's really earth abundant materials, and it's also very stable. So for a lower cost battery due to a less restricted supply chain, LFP, which is a type of lithium ion battery cathode, is getting a lot of attention. You can also move to oxygen gas or sulfur for your cathode, but this leads to, you could technically call these lithium-ion batteries because it is a lithium ion that is doing the back and forth motion, the shuttling inside of the electrolyte. But when you have oxygen gas as your cathode, that is a lithium air or lithium oxygen battery, sulfur, lithium sulfur battery. These are, I don't think lithium air is commercial anywhere. Lithium sulfur is getting to be commercialized right now. These are highly sought for maybe aviation applications or really high energy density applications, not for grid applications. Now, the electrolyte is super important. This is what shuttles your ions back and forth. In lithium-ion batteries, this is strictly non-aqueous, which does lead to the flammability issue. A lot of people are moving to solid electrolytes in research. There's an assumption that that leads to greater safety. That is an assumption that is somewhat proven, but not exactly borne out. So there's still a lot of research on doing that. Moving to solid electrolytes is great, but I don't see that for grid applications because of the high manufacturing costs at this time. Here are some research goals that I just wanted to pick on for today. More silicon in the anode, particularly for electric vehicles, because you want the high energy density. Stabilizing alternative cathodes is sought. So when lithium goes into a cathode, one of the transition metals changes its oxidation state. And the goal now is to get more changes in the oxidation state of the cathode transition metals or the anion lattice in the cathode. Stanley Whittingham himself is one of the people working on stabilizing these alternative higher energy cathodes. Fast charging, more important again for transportation. The switch to sodium ion. It's not a one-to-one switch to go from lithium ion to sodium ion, but it's the same format of a cell. It's the same kind of manufacturing processes. It's just sodium instead of lithium. And there is hope that this will be lower cost and maybe good for low temperature performance and just lower supply chain restrictions, because sodium ion cells do not seem to be relying on the expensive transition metal oxides. Recycling and reuse is also a giant area of research, which is necessary if you are going to meet the demand that we have coming up. Here's some information on lithium-ion battery recycling, but for more information, I want you to see the ReCell Advanced Battery Recycling Center, headed by Argonne National Lab, funded by the Vehicle Technologies Office. There are 3 known processes really for lithium-ion battery recycling: direct, hydro, and pyro. We always start with mining, refining, cathode production, battery manufacturing, following this blue curve. When the battery gets used, there's a few options. One of the options is not in here, which is the drawer in your bedroom that you never open, but it can go to the landfill. It can be used for second life of car batteries for grid applications is a burgeoning area, or you can recycle that battery. This is absolutely necessary. However, we do not have producer responsibility and core charges as a uniform thing in the United States right now. Globally, this is something that there is a need for. We need a circular lithium-ion battery economy to keep the prices down and just to meet the demand that's coming. The price of lithium-ion batteries is so low right now, and I can't see it getting any lower just due to how the demand for multiple applications is just continuously skyrocketing. But the goal for ReCell is to enable this direct recycling loop. And for more information, there's the Federal Consortium for Advanced Batteries, National Blueprint for Lithium Batteries, if this interests you, and the new LiBridge Public-Private Alliance, which is kind of administered by Argonne, but and there are convener organizations of NatBat and New Energy Nexus, New York Best. They work with industry and FCAB to kind of work on the supply chain issue and keep information flowing. So I want to just end by saying we have a diversity of energy storage options highly needed. What you're looking at here is from the International Energy Agency Net Zero by 2050 report. Astonishingly, for us to get to net zero by 2050, we need overall 8% less energy demand in 2050 than we need now. But there's going to be 2 billion more people. So this could be an issue. The STEPS program is a stated energy policy scenario. So if every stated policy got into effect, this is what the gigatons of CO2 emissions would have to be for us to get to net zero. And what I want to point out here is that there's an energy storage type, not necessarily electrochemical, needed by every single sector here. We've talked a little bit about transportation and electricity, but there's also industry and buildings. Now, also, as renewables grow, and they will be growing steadily, energy storage needs to grow as well. So energy storage, batteries and renewables are a perfect pair. And the best energy source is always a case-by-case basis. You can see by 2050, the use of oil and coal will have to dramatically reduce, while wind and solar will be going up and up and up. So paired with wind and solar, we need more energy storage. I'm over time, so I will just leave this here to say that lithium-ion batteries are seeing a lot of competition for and from non-electrochemical energy storage options, when you start talking about long duration storage, which is a very hot topic. You probably heard about that yesterday if you were here. And as you have more and more and more renewables on the grid, you just need so much more energy storage to pair with that for robustness. And the organization I work with, J. Caesar, one of our startups that we inspired was Form Energy, which again was talked about yesterday, which is a flow battery technology. I'd like to say thank you. And for more information, you can find information at jcaesar.org or email me anytime. Thanks.
Thank you so much, Lynn. That was a great presentation on lithium-ion chemistries, although I can't imagine how much more you would be able to share if you had more than 15 minutes. I was particularly fascinated with the many trade-offs between the chemistries that impact safety, affordability, and their technical application. So audience, please be sure to put your questions in the chat. We'll get to them during the group discussion at the end of the presentations. Next, it is my pleasure to introduce Mayana Kamara. Mayana is responsible for the North and South America division of BASF's Stationary Energy Storage Division, which distributes sodium sulfur battery storage systems. Their company recently installed their long duration storage system at a nickel copper cobalt mine in Western Australia, where they're piloting their scalable modular base unit of 250 kilowatts by 1.5 megawatt hours, ultimately designed for installation at the gigawatt scale. Mayana is based in New Jersey and has been with BASF for the past 12 years, working in a broad range of roles from regulatory to sales to project management. I'm amped to hear what you have to share, Mayana. Take it away.
All right. Good morning and good afternoon. So again, my name is Mayana Kamara. Again, good morning, good afternoon, depending where you're calling from. Been with BASF for 12 years. I'm the sales manager for our sodium sulfur batteries, and here we go. So at a glance, I just want to just review exactly who we are as a company. BASF is one of the largest chemical companies in the world. In 2022, we had sales of 87.3 billion. Our EBT for 2022 was about 6.9 billion. We have 232 production sites and 6 Verbund sites, and around 90,000 customers in various sectors. And these various sectors range from chemicals, range from personal care, agriculture, different divisions, and even our catalyst division that concentrates on batteries, but for cars. When it comes to who we are as a company in terms of batteries, we're very active on different levels. So we actually make the cathode materials for lithium-ion batteries that focuses on e-mobility. We also have some plants in Germany and also in Finland and China that invest into creating this cathode materials for lithium-ion batteries, and also recycling plants as well in Germany as well. Now, specifically with my division, which is a sodium sulfur battery, BASF is the exclusive distributor of the NAS battery, which is produced by NGK. NGK is located in Japan, and BASF is allowed to distribute these batteries all over the world, except in Japan, UAE, Hungary, and Taiwan. We are, again, our focus is to be able to work with our local BASF offices and also with our sales agents to sell these batteries worldwide, except those 4 countries which I have mentioned. So this next slide gets into the relationship between NGK and BASF altogether. So again, these batteries have been manufacturing for more than 20 years by NGK. BASF has years of experience when it comes to research and development in sodium sulfur battery, and now the two have joined forces together. And what I mean by that is that we are now the exclusive distributor of these batteries, except in the 4 countries that I mentioned. And then also we're working on the next generation battery, which is actually available this year and going forward. So this is now BASF's chemistry and NGK chemistry into one battery. So this is the relationship between us. Now, what exactly do we offer here? This is a long duration battery, meaning that it's anything greater than 4 hours. That 6 to 8 hour that you see right there is our sweet spot. Our sweet spot means that this is where our battery functions very well from a technology perspective, and also from a pricing perspective, we're very competitive in this range. It is also a long lifetime battery. So this is a 20-year, 7,300 cycle, whichever comes first. Also a very safe and reliable battery. We've already gone through our TÜV Rheinland certificates, and also we have our UL certification as well. We have the 1973 and the 9740A as well. It's an environmentally friendly battery. So what that means is that the components that make this battery are literally sodium, sulfur, carbon, aluminum, materials that are found very easily, and we're not really struggling for the raw materials at all. And the prices are very stable. It is also a high energy density battery. So that means that if you stack the batteries on top of each other, you're able to increase the megawatt hour. It is also a very fast response battery. It's climate resilient, and we have these batteries located currently in Abu Dhabi and also in Canada. And the one in Canada has been there for a while. It's actually the ambient temperature for our NAS battery is -20 to 45 degrees C, plus 45 degrees C, which I'm sure will be very capable to handle the weather conditions in Alaska. It's also a very low maintenance battery. So what that means is that it requires minimum care. So it's minimum preventive maintenance that really plays a significant difference in the cost of owning such a battery. Now, where can these batteries be used? We have different energy market segments. So whether it's in the power generation all the way to microgrids. So if you're trying to, whether you have arbitrage needs or ancillary services, or maybe you're looking for backup power, you're looking for 24/7 power supply or time of use shift or even peak shaving. These are all the different market segments where our NAS batteries currently play a role or could play a role in the future, depending on the customer's needs. Now, looking at the battery design from cell to container, let's start with the cell part of it. This is a 50 centimeter by 9 centimeter battery. So what's in it? It's you have your sodium, you have your sulfur, and you have your beta aluminum ceramic. There's 192 of these cells that are then put into a battery module. That battery module is about 2 tons, and there are 6 battery modules that are then enter into a container. So it's already a containerized system. There's minimum fixing when you get the container on site. But basically, the container is 21 tons. And for one container, which is a 20-foot container, it's 250 kilowatt, 1.5 megawatt hour. This is also a very high temperature battery. So you're looking at 290 degrees Celsius to 360 degrees Celsius. The operating temperature is around 300 degrees Celsius. And again, it's a long lifetime battery, which is looking at 7,300 cycles or 20 years, whichever comes first. So this is really the battery design from cell to container. This is a up close picture of the battery container. As you can see, there's 6 modules in there. The battery does come with the BMS system, which is a separate room for that. That room does have a small air conditioning, but overall, the battery system itself does not require any AC. And then also what I forgot to mention is that there's sand in between each of the cell, which absorbs the heat. And that's a safety mechanism for the cell. So this is just some specs about the container overall. All right, here are some up close pictures of the control unit and also the rear side of the battery. Those are the modules on my right-hand side right here with a small fan on each unit. Again, here are some pictures of the front side of the battery and also the rear side of the container. As I mentioned, it's a containerized system that's already coming together. So it's minimum fixing that has to be done, but it's really a containerized system coming all together as one piece. All right. So in terms of safety, these are some of the tests that have happened with TUV Rhineland. So as you can see here, from external short circuit all the way to drop in the battery, the common denominator that you see with all of these different tests is that there was no cell damage inside of any of these tests. So whether it was exposed to fire or was submerged in water, none of the cells were damaged inside the module, and there was no leakage as well. All right, so here's a chart just showing all of our installations thus far. As you can see, clearly in Japan, we have the largest installation of greater than 400 megawatts. Moving over to the Middle East, that is the project I was speaking about earlier that's in Abu Dhabi. We also have a very interesting one in Germany, which is a NAS battery and a lithium battery to combine as one. It was a demonstration project to show that both technologies can work side by side. We have some installation over in Europe as well, and then also in North America. We have one in Kathleen Island, which has been there since 2011, and the entire time it's been there, it's only had one cell failure out of the many cells that are in the module. But yet the container is still working, even though it had that one cell failure. We have more than 250 projects and a total output exceeding 720 megawatt, 4.9 gigawatt hours so far. Here's our largest installation that we've done in the world. It happened in Japan. It's 252 containers. The capacity for this was 50 megawatt, 300 megawatt hour. It took about 6 months to construct this, and the main purpose of this was for renewable energy. So what does the total cost of ownership look like? I always explain to our customer that you're going to start from CapEx all the way to end of life. Of course, you're looking to see exactly what this battery system costs, which is, of course, your CapEx, but then also to keep in mind that this is a low maintenance battery. The degradation is less than 1% per year. It requires no AC. It's also a very long lifetime battery, up to 20 years or 7,300 cycles. The components are easily found, recyclable or reusable as well. And overall, from CapEx to end of life, these are all the components that go into the total investment of owning such a battery. And this is my last slide here. So what is our key message to our customer? This is a high energy battery, a long lifetime, safe and reliable technology, environmentally friendly components, climate resilience, more than 250 projects worldwide. So this is a proven technology that's been around for more than 20 years. And BSF is now the exclusive distributor. So we are here to serve each and every one of our customers' needs, no matter where they're located.
Very good. Thanks, Mayana. I appreciate it. I did not realize that you have an installation on Catalina Island. I spent a little bit of time down there, and I'm very curious to learn more about that. So if we have time for me to ask a couple of questions, I may poke that and see what the application there is. Nor did I realize that you require no AC. So I'm sure there's going to be some questions about that as well. So I'm interested to learn more, as is our audience. We have questions coming in that we'll save for the end of our panel. But next up, we'll wrap up today with Mark Higgins. Mark is the president of North America and the chief commercial officer at RedFlow, a zinc bromine flow battery company based out of Australia. RedFlow was recently approved by the California Public Utilities Commission as eligible for the state's self-generation incentive program that provides rebates for storage systems that can meet all or a portion of the electrical energy needs of a facility. Notably, RedFlow is one of the very few non-lithium-ion energy storage providers to have received this approval. Mark himself is a globally recognized leader in energy storage strategy with deep connections throughout North America's energy ecosystem. He has served as chair of the U.S. Department of Commerce's Renewable Energy and Energy Efficiency Advisory Committee, co-founded and serves as venture partner at Resilient Earth Ventures, and is the former COO and board member of Stratagen, where he ran the company's global consulting business and managed the operations. I'm sure Mark is charged up to tell us about RedFlow's form factor, how it compares to lithium and other flow battery chemistries, and how it will work in Alaska. It's all yours, Mark.
Good morning, everybody. Thank you so much. I am delighted to be here and am looking forward to telling everybody a little bit more about kind of one of the emerging technologies in the non-lithium battery space, specifically talking about flow batteries today. There are a variety of different types of flow batteries, and so I'll touch on some of all of them, but what I know best is of course, the zinc bromine flow batteries, because that's what RedFlow does. First, I'm going to start with a video, and apologies if this is a little bit marketing heavy, but it is, I think, a really good and succinct explanation of how zinc bromine flow batteries work and why they have a lot of advantages over some of the more traditionally used battery chemistries that are on the market today. So let my video explain itself.
RedFlow is leading the clean energy transition by delivering one of the world's safest, most sustainable energy storage solutions. Our patented flow battery uses a liquid electrolyte contained in 2 separate tanks to store energy from renewable power sources. To charge, electrical energy is utilized to pump electrolyte through the battery and drive chemical reactions within a stack of cells. This reaction occurs in 2 half cells in the battery stack. In one half cell, zinc ions gain electrons and are plated out as metallic zinc on the electrode. In the other half cell, bromide donates an electron and is safely turned into complex bromine on the other electrode. The reaction is reversed during discharge, as the zinc and bromine return to their original states, with metallic zinc dissolving into zinc ions in one half cell and complex bromine becoming bromide in the other half cell. In the process, electrons are released to provide an electrical current. There are many benefits to this technology. The batteries can discharge completely without damaging them, and they can stay in a charged state indefinitely. The design of the battery and its underlying chemistry yields an extended lifespan. The battery materials are recyclable at end of life, and they are safe and non-flammable. Designed for scalable, high cycle rate in medium to long duration applications, Redflow's flow battery technology is the safe and reliable energy storage solution.
All right. Well, that's just a little bit about our technology. What makes zinc bromine batteries different and flow batteries in general a little bit different than lithium-ion technology that is traditionally what you're seeing on the market out there. So I think one of the characteristics that really make flow batteries a bit different than lithium-ion batteries is around battery performance for the grid. So they don't degrade over time in the way that a lithium-ion battery degrades over time. They generally have a full depth of discharge. That's also differentiated. You don't have to oversize them to account for that kind of narrower range of depth of discharge that you have with the lithium system. They generally, as I mentioned, have they like to do the daily cycling. You don't have that kind of energy output degradation over time. They do a great job in kind of extended duration applications. The optimal duration for our batteries is really anything over about, I'd say 3 or 4 hours. If you're doing daily cycling applications, you can do up to 12 hours pretty easily. We have a unique feature in our batteries called the hibernation mode, which allows us to essentially shut down our batteries, no self-discharge. So you can stagger the discharge over, days or weeks, or, use it as a backup power supply. So it just stays fully charged for, months on end if you need to. That's something that is, pretty unique to our particular chemistry and our battery in particular. We also have, just like our sodium sulfur batteries have a much wider operating temperature range. We do too. We have the ability to operate in, kind of I'd say more like freezing up to about 45 degrees C without any sort of heating or cooling. So that is quite a bit wider than you have for lithium ion. In a cold weather environment, you'd have either heating in the enclosure or you do an indoor enclosure. In a hot weather environment, honestly, we've never even installed an HVAC system in any of our installs to date in hot weather environments because they do perform so well in warm temperatures. You don't have a risk of thermal runaway with zinc bromine batteries. And we're also, similar to sodium sulfur, dealing with a very abundant, very recyclable, very non-toxic set of materials that really just don't present a lot of the challenges that lithium does from a supply chain. Bromine is readily available, for example, in the United States. The U.S. is one of the main places that mines bromine for use in chemicals. Zinc is also available very readily in North America as well. So we can really help with our own supply chain in using more of the zinc technology. So I wanted to just get a little bit to what differentiates the different types of flow battery chemistries. So zinc, bromine, iron, and vanadium are the 3 typically used mineral types that you see in flow battery chemistries. Zinc is probably the highest in terms of energy density and power density across the different chemistries that you can have within flow batteries. It has probably a slightly higher price profile than, say, an iron flow battery does, but not much. It's still actually one of the cheapest potential materials you can use in batteries, far, far cheaper than lithium ion, far cheaper than vanadium. That would be the other one, which is a much rarer mineral that you can use for batteries. You got a very stable price profile, just due to the abundance of both zinc and bromine. It also requires some chloride in it. That's generally pretty stable in terms of price as well. One of the issues with flow batteries and zinc bromine batteries in particular historically has been around dendrite formation, just like with the lithium. Early generations of lithium batteries had that. as a challenge as well. And those have been very well addressed within our chemistry through what's called a maintenance cycle that we go through that strips away all the zinc off of the plating that we're using within our stack. It's got a design that allows, as I mentioned, that hibernation mode. And these batteries have been installed now for well over a decade in many different settings. Zinc bromine batteries are very commercially proven in lots of different operating environments. In fact, RedFlow alone has more than 250 installations in all sorts of different harsh environments around the world. So very, very familiar with managing a lot of the issues that come with harsh environments. So just a little bit more about iron batteries. As mentioned, that's an abundant, low-cost material. One of the things that you typically see with iron batteries that can be differentiated between zinc is that typically an iron flow battery, you'd fill the tanks on site. Zinc bromine batteries, you can either ship them with the electrolyte already in them, or you can fill them on site. It just depends on what's optimal for the site. pH management is an issue with both zinc bromine and vanadium batteries. And there's a little bit less operational experience on the iron side. Vanadium has a pretty comparable operating experience to zinc globally. And really, I think in a lot of respects, vanadium and zinc bromine batteries have a very similar operating profile. They have a very similar round trip efficiency, et cetera. Really the key difference, energy density, where zinc is the highest energy density of these three chemistries, and around kind of raw materials pricing. So this is actually about our system. And one of the things that makes RedFlow unique is that we started with a very small battery module. This is a 10 kilowatt hour module that we use as the building block of all of our systems. We've got, it's a very simple design. It's got a stack on the top. It's got a control box. It's got a tank. It's got pumps. It's got fans. Pretty straightforward. How we get to bigger systems is through pods. This is a 200 kilowatt hour enclosure that is one of our standard building blocks that we use for systems worldwide when we're not doing them indoors. And then we just kind of, very similar to what you see for lithium-ion, put this in kind of rows, and you can build a big, quite large system, multi-megawatt hour system out of this very easily. This is an example of one of our systems that's gone in Southern California. It is a 2 megawatt hour installation that's at a bioenergy facility. This provides both resilience for the site, as well as kind of a load following resource to help them manage demand charges. And then during peak energy periods in the evening, it discharges to allow kind of minimization of grid consumption during peak energy prices. So Alaska is obviously a harsh environment, just like a lot of the environments that we've deployed in. And I actually really like this picture of a surfer kind of out of his element, just making it work in a new environment. Partially because I think it fits the bill of RedFlow as an Australian, Californian-based company, but also fits us because most of our experience developing projects is in extreme environments. Now, granted, those are usually in the opposite type of conditions. But I think through sufficient preparation, our big lesson in all of those projects has been that through sufficient preparation, we can design a system that's going to work in the harshest of environments. And I also like this because I'm personally surfing myself, and really you learn in that kind of environment when you're out there and in nature that you really have to be prepared for all different conditions and make sure that you're accounting for all potential contingencies out in the world. And so how do you think about adapting a flow battery for extreme cold environments? Well, first of all, we have to think about the electrolyte. That's item number one. It is a water-based electrolyte. Our chemistry is a saltwater-based environment. Bromine is a salt, and electrolyte can freeze. So how do you deal with this? Well, salt water generally has a slightly lower freeze point than does regular water. That's the first thing. And you can reformulate the electrolyte to reduce that even further. Enclosure heating is an obvious thing that you can use to deal with that. And indoor enclosures are probably the other thing that you would be considering, just like you would for many other types of infrastructure projects in Alaska. You'd be putting them indoors when you have some concerns about them being exposed to the elements. Zinc bromine batteries are actually very, very well suited for indoor applications because they don't have that risk of thermal runaway. You have to have some ventilation in place, but generally speaking, an indoor installation works quite well for zinc bromine. And like I said, in an outdoor environment, what we do is you just make sure that that enclosure is heated properly so that the system itself can stay above the freeze point. Transportation challenges are obviously also kind of an issue in Alaska. The good news when you're dealing with zinc bromine, at least, is that it is the most energy dense flow battery chemistry that's on the market. So you aren't going to have to be dealing with as much material, as big of a volume when you're trying to get battery systems in place. We have a very modular form factor, so it can be moved around very easily in trucks and lifted with a forklift. Those 200 kilowatt hour battery enclosures that you're seeing, you can fit multiple ones of those easily within shipping containers or within those kind of standard things that you'd see in a semi. Reliability also, I know, is going to be really important when you're dealing with remote environments and remote communities that need to have systems that just work. And so when you're looking at the technology that you're using and the companies that you're working with, you want to make sure, just like our colleagues at BASF, you've got a robust operational track record. You have low occurrences of failures that could cause systems to go out. That's going to be really important. So you want to ask for data on failure rates. You're going to want to look at their O&M program, what they have to do to keep batteries operating well, what the vendor solutions would be for doing O&M in a remote location, I think is really important. I think that there's a lot of unique considerations when you're putting systems in remote locations and in harsh weather environments. So that's just a little bit about our technology and kind of how we would work in harsh environments such as Alaska. And I would love to turn it back over to the broader panel now for any questions that folks may have.
Thank you for that, Mark. We'll let the panelists come up on screen with me here. We do have a few questions from the audience. Some of them got a little answered on the way there at the end, Mark. And so maybe I'll just start with you because there was a few from the audience about the Alaska market in particular, starting with, and I think I know the answer, but can the flow battery be charged in one season, in other words, the summer, and be on standby until the winter before discharging without a problem?
Absolutely. Our batteries, because of that hibernation mode that we were just talking about, have that ability to be charged. And once you put them in hibernation mode, they can stay that way indefinitely at 100% state of charge.
Does that require any standby of the electronics, or would it be a kind of a hot standby, if you will, in that hibernation mode?
I think the main consideration for Alaska is probably going to be around that heating element that we would need to have to make sure that you have the thermal management so that the electrolyte doesn't freeze. As you're heading into winter, you're going to have more of those cold nights. And so that's the element that you'll have to deal with.
Thank you. Lynn, I've got a question from you, or a question for you from the audience about salt water. Are you able to provide any comment on the potential for using salt water as an energy storage base or property?
I'm not, but I'm going to put something in the chat that I found because I read that question. This is work funded from the Office of Electricity. Anne-Marie, who talked yesterday, funds this work. This is a presentation from Oak Ridge National Laboratory exactly on saltwater batteries for, I think, mid or long duration storage.
Reading the audience's mind, we have a little bit of salt water around Alaska, so I can imagine why that would be of interest.
Yeah.
Miana,
yes.
For your sodium sulfur batteries, are there any installations using excess heat from the system for ancillary thermal loads?
Yeah, I saw that question as well, and not that I am aware of, but what I will suggest, and I think the question came from Mark, if I'm not mistaken. I can definitely follow up with technical, and if Mark wants to reach out to me, I can provide my email and get that answer to them, but I'm not exactly sure. I'm not too sure.
Yeah, just to follow that up with a comment, definitely in Alaska, heat's a very valuable resource for us. We spend a lot of time and engineering effort capturing the waste heat from the diesel power generators in our remote power systems. And so, especially as we move towards high penetration systems, thinking about turning off those diesel generators, we actually need to replace that heat sometimes. And so if there is an opportunity to use the waste heat from a storage system, then I think we're going to be very interested in leveraging that as well.
Of course.
Back to you, Mark. I'll just kind of go around robin, if we will. I'm curious about your energy pod. I couldn't quite tell from the design if the container also included the converter, but I assume it does.
Yeah, so typically we design our energy pod containers to include DC-DC conversion so that you can have a higher voltage DC output. We also can we also can integrate in inverters. We've used like solar converters in particular to take the DC voltage, the native DC voltage of our batteries, and output an AC power supply that can be directly connected to lower voltage, smaller installations typically. So it just depends on whether you're looking for a kind of more of a utility grade AC inverter solution or more of a small commercial or residential or type of AC solution. Because when you have the small, the smaller inverters, those integrate well directly with our batteries. Otherwise, you have to do the step up in voltage.
As a follow-up to that, then I'm curious. One of the challenges in remote Alaska, in particular, is the transportation and the availability of something to not just get it there, but to get it off the equipment and then to the site. So do you ship your energy pods fully populated? Does it come separated from each other? And is there any installation required?
We ship our batteries ready to be hooked up, basically. That's typically how we would do it. We have the ability to ship the battery modules dry, which can be advantageous if, for example, they need to sit outside for a long time in cold before they're going to be installed, because just to avoid that electrolyte freezing. But typically our installs will ship them just essentially ready to be dropped in place and hooked up to whatever system they're being hooked up to.
Awesome. Thank you. Lynn, back to you. You mentioned resell in the context of recycling resources. Is there anyone that is responsible for developing the standards for recycling, in particular for the manufacturers? Where do we go for that sort of information, and who's working on that?
That's a great question. I'm not exactly sure, but I know that LiBridge is concerned about things like this, and consortiums are being formed to do this. So maybe FCAB, maybe LiBridge, maybe there's somebody online right now who has a better answer to this. The lithium-ion batteries are not at the same state that lead-acid batteries are. Lead-acid batteries are very organized. They know exactly what's going on. They have core charges. They have labeling requirements so that things can be sorted very easily. I think that's all pretty nascent for lithium-ion batteries, and we all have to collectively, globally connect on this level. So anyone else have input for that? I would love to see that myself. Please put it in the chat.
All right. I'm just noticing as we're getting a few other questions coming in the chat, and I'm, of course, speaking with our panelists and trying to keep track of it as well. If you would, please identify which panelist you may be asking the question for, so that I can make sure I'm addressing it to the correct panelist. Miana, can you tell me more about the weatherization that would be required for, I think you mentioned below 20 C ambient temperatures. Obviously, there's a few locations in Alaska that get lower than that. I always like to joke that the first question's always about temperature. And even the best manufacturers beat their chest and say, well, we do negative 40 C. The second question then will be, what about negative 50? So I think it's a little bit of a challenge that we like to pose, but I am curious how you would address the cold temperature installations in Alaska.
Yeah, so we actually did the installation in British Columbia. I actually have a paper that I can also share. It's a public paper about that installation in Canada, where there were different options that were mentioned for this installation, and the solution they ended up leaning towards was basically creating a prefabricated building to help protect the battery from the weather. Also, what NGK did was they modified their battery module to be able to withstand such harsh climates. But I do have a paper that I can publicly share with folks to read of all the different options that were suggested and which one they ended up picking to do for this specific project.
I know our audience would be extremely interested in that if you're willing to share it. As a follow-up to that, aside from the temperature, especially when you're putting this now into an indoor enclosure, is there anything else you have to address? Mark mentioned ventilation, but I'm also thinking of fire suppression and safety systems when you're putting this into an additional enclosure.
I would say, of course, fire is always a concern. One thing that we've installed in our batteries, as I mentioned earlier, is that we do have sand in between each of the modules, which prevents from fire thermal from runaway from fire spread into the next module. So that is a safety mechanism that we've installed. Also, in our advanced module, which I can share under NDA, we've put in 2 new changes, I guess you can say, that also help with preventing fire and also improving the battery's degradation. So I would just say that, what I can publicly say is that the sand is a very, very key part of our battery that prevents fire from spreading, which is something that we should all be concerned about. So.
Awesome. Thank you. And Mark, I'm going to ask the same question of you. Like I said, you mentioned needing additional ventilation for an indoor installation. I guess I'm curious, does your energy pod go directly into an installation, first of all? And then second of all, is there any other considerations around fire suppression, safety, or other systems that are required for indoor installations?
Right. So NFPA 855 generally covers the guidelines that are necessary for dealing with kind of fire, spacing and setbacks and things like that. Typically, there's some discretion from the permitting authority around what sort of requirements they'll put in place around fire suppression. We typically have not seen a significant amount of fire suppression required for our technology because our electrolyte is water-based. It doesn't catch on fire. We've done the 9540A test. We're not even required to do 9540A anymore because you can't burn water, right? So the fire suppression is really more around the power electronics themselves if you had a short or something like that, but not around any sort of thermal runaway risk.
Thank you for that. Lynn, I'm actually going to ask you a similar question. Of course, it's unfortunate perhaps that even the general public's aware of some of the fire issues around lithium-ion. I'm curious, are you aware of any resources? Mark actually mentioned something that I think we have to address very frequently, and that's the authority having jurisdiction. They're typically not educated on any type of storage chemistry, but lithium-ion being the predominant one. What are the resources that are available that a community, an AHJ, a municipality or a utility should be looking to when thinking about safety and fire suppression?
For lithium-ion batteries, a giant lithium-ion battery installation shouldn't go in without coordination with local fire departments. Local fire departments need to be trained onto exactly where the location of the batteries are, what's in them, and they need a special type of, I think, class 4 fire extinguisher or something of the like to put out those fires. So it's really just having the public be aware that if a car is on fire, stay away from it. And whenever these types of fires happen, the fire department has to have previous knowledge that these are the batteries right there. So coordination with fire departments and keeping a strong distance. Lithium-ion batteries, the small ones that we see causing little fires, that could be due to people operating them outside of their operating conditions. Any sort of mangling of what you bought should not happen. These are not something to take apart in your kitchen. There was fires in New York City, I think, because people had scooters inside their apartment and they were trying to do work on them inside. This is not apartment work. You are not supposed to touch them. And fires that have happened for lithium-ion batteries sometimes can be due to the incorporation of too much silicon too fast, because silicon is a new material. It gives you better energy density, but it also expands and contracts. I think it was the Galaxy Note or one of the Samsung Galaxies that was recalled due to fire, just due to spatial specifications that could not contain the expansion of the new technology. But really coordination with fire departments and keeping away from that type of fire. Awesome.
Well, that brings us to the end of our time. I think that's a really great place to stop. And I am going to summarize just with one more point. You mentioned coordination and education being the other, both the users as well as the AHJs and fire departments. So with that, I'd like to thank you, Lynn, Mark, Miana, for your time. Really enjoyed it. I have a ton more questions, as does our audience. Thank you for the resources that you've offered and put into the chat. And for the questions that are outstanding from our audience, I would encourage you to reach out to our panelists and see if they can address them with you directly. With that, I'll turn it back over to Jeremy.
Hi, thank you. Thanks, Rob. Thank you, Lynn, Mark, and Miana. Yeah, that was fascinating. We learned a lot from that. And thank you for all the attendees and all your questions. It is now my pleasure to introduce you to the moderator of our next panel, where we'll be looking at thermal energy storage. Please help me welcome Dave Messier. Actually, he pronounces it wrong. He pronounces it Messier, I believe, but it's a good French name, Messier. Infrastructure Division Director of the Canada Chiefs Conference. Dave has been working on energy issues in Alaska's interior for nearly 15 years, serves on the board of Golden Valley Electric Association, and through his side business, Daylight Energy Services, has designed and installed a number of lithium-ion battery energy storage systems on remote Alaska energy grids. He lives and works in Fairbanks. Dave, as a true Alaskan, wears many hats, and I'm not sure how he manages to do everything that he does. Dave, we're really glad to have you with us, and the floor is all yours.
Thanks so much, Jeremy. And I appreciate the context on my last name. As my grandfather told me, he's like, people try to tell me how to say our last name all the time. And I tell them it's my last name and I'm going to say it however the heck I want. So I really appreciate ASEP for kind of putting on this panel. I hope everybody on the line has gained a lot from the last few days of presentations. I know I certainly have. It's been great to hear the different energy storage technologies and the different presenters discuss. And I really appreciated Rob's perspective of some of the, older, I guess, technologies that have been around for a long time, because I think it's good for everybody to have that historical context. I know from my world, both sitting on the board of Golden Valley and looking at some of the larger options for renewable energy integration and what that requires as far as long duration energy storage. And then also with my Canada Chiefs Conference hat, trying to implement these shorter duration energy storage projects in remote Alaska. I'm really well versed in all the challenges that both the rail belt faces in regards to cost and scalability and also temperature. And then also rural Alaska, where there's a huge need, very high energy costs, and there's huge issues with scalability and all the other challenges. So I appreciate everybody's time, and we'll kind of kick it off. We did make a little challenge to presenters to throw in some jokes about batteries. And so Rob Royce gets some extra points for all of the puns. Those were fantastic, Rob, and you are a mentor to me in many ways. We're going to start with a presentation from Robert Bernard. Robert is the Global Director of Energy Storage for Westinghouse, and he's got over 20 years of experience in the power industry, currently serving as the Global Director of Energy Storage for Westinghouse Electric Company, LLC. Prior to that role, Robert successfully led various business segments within Westinghouse, including plant modifications, major programs, and turbine services. Rob also spent several years based in Paris, France, managing a multinational consortium responsible for major upgrades to the French nuclear fleet. And in his current role, he's responsible for the global commercialization of cutting-edge energy storage technologies as part of the Energy Systems business unit within Westinghouse. So without further ado, I will hand it over to Robert Bernard. And good luck with the presentations, Robert. I'm looking forward to it.
Thanks, Dave. Appreciate it. Good morning, everybody. Appreciate the time. I wanted to take the opportunity to talk a little bit broadly about thermal energy storage and use what we're working on as a means just to get folks think is what it can be, and really energy storage in general, addressing all the challenges that were discussed yesterday and have been discussed today, how we're going to get there from here. What are some creative ways to do it? I think as we've all heard, there's a lot of challenges and a lot of opportunity in this market. And Westinghouse is an energy company, primarily a nuclear energy company for the past 30 or 40 years. And so it's been very interesting to watch the the shift in power markets, particularly in the United States, and the transition as things have gotten quite a bit different over the past couple of decades, created new. So from Westinghouse's perspective, we've been able to watch in quite a bit of detail the evolution of power markets. Being primarily a nuclear energy company, we've seen things emerge over the past couple of decades as renewable penetration has increased, as electrical loads have increased, things for our nuclear customers that we probably couldn't have imagined happening 20 years ago, to the point where, what was almost unfathomable of a nuclear plant having negative power pricing scenarios, or having an excess of energy that needs to be dumped because there's nowhere to put it, no way to store it. These are the type of things we see. Again, they vary from region to region. And there are a lot of challenges that we believe are going to be met with a lot of technologies and a lot of different solutions. And it's been great to hear about all the different technologies here over the past couple of days. So we are looking at energy storage similar to today's, maybe a historical generation scenario. You had a generation stack. We have a mix here of nuclear, coal, gas, an increasing proportion of renewable energy. We have a certain amount of hydropower in the U.S. that has existed and hasn't, right or wrong, hasn't changed that much over the years. Energy storage is going to look the same. There's going to be different tools that are going to be best suited for challenges, for different regions, for different use cases. We had a nice conversation yesterday, I heard of on pumped hydro, and it's a great example of a technology that can solve a lot of use cases, but is limited by how and where it can be installed. Thing we want to start to think about here on these technologies, and I don't think I've heard it too much here, is how, as you look at energy storage and you look at the traditional technologies of lithium-ion batteries and other things, where you have a coupling of the power capacity of a particular solution and the energy capacity. And that's why, due to the design of lithium-ion, they're extremely well suited to durations up to 4 hours, but the cost can become prohibitive as you go longer and longer in duration. We're talking about a lot of technologies here that decouple those things, that decouple the amount of energy I can store versus the amount of power I can actively put on the grid. The discussion yesterday on megawatts versus megawatt hours. And if I get to a point where my means of storing energy is decoupled and ideally quite cheap, now I can extend durations, I can solve more challenges on the grid, and I can do it at an increasingly low cost. And we've seen that with the Department of Energy, the Energy Storage Grant Challenge right now, with the target of 5 cents a kilowatt hour for levelized cost of storage. We see it in the financial use cases around the country. We see all the drivers to get longer storage, but also cheaper and cheaper. So Westinghouse, I'm going to use the technology that we've been developing, not here as a sales pitch, but just as a guideline of thinking about thermal energy storage, as I mentioned, and how it can be used and what it really can look like. And I'll just give a little bit of background. I mentioned a moment ago nuclear power plants in what was once a situation that was unthinkable of having to deal with varying load. And a nuclear power plant really wants to be run at 100% load 24 hours a day. And you look back about a decade ago, some of Westinghouse's nuclear utility customers, particularly in California, started to experience some of these challenges of needing to try to load follow a bit. At the time, Westinghouse started to think, well, how can we come up with thermal energy storage that could be integrated into, let's say, a nuclear plant, maybe a coal plant, where I could take some of that steam in the form of heat, store it, and adjust the electrical output of my plant while my reactor or my boiler was operating at full capacity. And then when the need was there, I could ramp up over 100% of production. How could I effectively, efficiently store that heat? And we started to develop a novel way to store heat in a concrete and oil configuration using what we considered sensible materials, low temperatures and low pressures, relatively speaking. We were admittedly a little bit ahead of the market of the need. We continued to develop the technology in the background. And today, with the new nuclear plants that we are deploying around the globe, that energy storage piece is a built-in design option into all those new nuclear facilities. And you'll see it now in the discussions on advanced reactors and small modular reactors, micro reactors, and having energy storage built in where I can flex the output. It's become a standard topic of conversation. And it's another form of energy storage, much like all these other forms we're talking about. It's allowing you to flex your power source on the grid. It's just doing it at the source versus necessarily coupling it with solar or hydro. So fast forward to now, along the way, we also looked at using this thermal storage technology in a standalone application. Electricity in, electricity out, as you would have with a battery or many of the technologies that we've been discussing here. And you may ask, well, I heard all these technologies yesterday. I heard talk of all these companies. I heard Malta with some heat that I didn't hear Westinghouse's name. As I mentioned, we're a nuclear technology company. That's how people know us. We've been doing this maybe intentionally quietly in the background. We haven't been out there. We're not a startup with this. It's an adjacent technology to what we've been developing. And we've got partners and we've got different ways we can integrate this with some of the other technology providers that were talked about. But what we're doing here, and I'll show a little bit clearer here in a moment, in terms of using heat for storage, we're taking electricity off the grid and operating a heat pump. And we have two reservoirs, a cold and a hot reservoir. And the analogy we like to make is that you think of pumped hydro that was discussed at length yesterday. I'm pumping water uphill and letting gravity have the water flow back down, generate electricity. Similar type of concept, but we're not pumping against gravity. We're pumping heat. We're pumping heat between a hot and a cold reservoir. And then we're in essence letting that heat flow downhill, if you will, to generate electricity. So we operate a large industrial heat pump that is going to move heat from a cold reservoir to a hot reservoir. And I'll get into those in a moment. And charge the system and have a large amount of energy stored. And then I'm simply reversing that cycle using mostly the same equipment. And this is large machinery that would be familiar to anybody who's worked in a power plant environment, and taking that heat, running a standard turbine connected to a generator, generating electricity, rejecting that extra heat back to the cold reservoir and bringing everything back to its starting state. To give a little more detail, what does that look like? What does that mean? So part of our criteria, as we've been looking at, how do you make thermal storage work? How do you make it cost effective? How do you make it efficient enough? These ideas, including pumped heat, right? These are not new ideas on energy storage. It's not new even to store heat in concrete, bricks, whatever material you may think of. But how do you do it a bit differently? And there's a couple things here that we came to over time. And one is the heat pump and the fluid we're using to move heat. So we're using a supercritical carbon dioxide heat pump and heat engine. And that carbon dioxide has properties different than your typical refrigerants, different than using air, allows us to operate at a temperature range that enables the use of what we call sensible materials. So in this case, our storage medium for energy is three primary materials. It's water, it's concrete, and it's oil. With that, we operate this CO2 heat pump. We move heat from water through a series of heat exchangers into a heat transfer oil that then transfers that heat into concrete. And that's where that's pulled from the technology we developed for nuclear plants. It's engineered concrete modules that are submerged directly in the heat transfer oil. There's no tubing, there's no piping. It's a direct horizontal thermocline wave through the concrete. It's a fairly simple, straightforward way of storing heat in a very effective way. And this is ambient pressure and it's relatively low temperature. It's 330 degrees C at the peak. And obviously the water is right around the freezing point of water at 0 degrees. That allows us to use, again, simple materials. We don't need to go into molten salts or glycol solutions or more expensive things. The idea here is how do you store heat at temperatures that let you do something really easy, materials you can find anywhere that you can procure anywhere, and materials that are relatively cheap. And as I mentioned, with that stored heat to discharge electricity back onto the grid, I'm taking that heat and letting it operate a heat engine cycle. Again, same equipment. The difference here is I'm running an expansion of the CO2 through a turbine versus a compression cycle when I'm charging the system. And I'm using regular turbo machinery that you'd see in any power plant, which has the benefit also of having rotating inertia connected to the grid, provides ancillary service capability. I can idle the unit when I'm not charging or discharging so that I can provide reactive power support to the grid. I can provide overall grid stability. This is an electricity in, electricity out, quote unquote, battery, but it really is more of a power plant. You think of it as a gas powered power plant for how it looks and operates. It's tanks, it's piping, and it's rotating equipment and turbo machinery. So relatively straightforward in its application and quite familiar to a utility in terms of how do I own and operate this asset. It's going to look and feel very familiar. And just a couple of final notes on this. And again, as I mentioned, there's integration with aspects of this system with other technologies. You're going to hear from Rondo shortly. There's integration there we've looked at. There's pieces of this that can be integrated into existing fossil power assets to better utilize those as we continue to ramp towards zero carbon emissions. But ultimately, the idea is low cost. And as I mentioned, we're talking water, concrete, and oil. So as I scale the duration, this becomes incredibly cheap from a storage standpoint. In our economics, 10 hours or more is going to be where this type of a system makes sense. That's where it's going to be economically viable. And the longer you go, the better that's going to look. And we could go up realistically up to a couple hundred hours, but from a practical standpoint in the near term, it's probably 48 to 60 hours at the maximum range, just from a footprint perspective. And it's relatively power dense at 1,000 megawatt hours on about 6 acres of land. But the limitation of this type of a system is that it wants to be big, right? This is not a type of system or type of thermal storage that can be deployed for 10 or 15 megawatt solutions or for shorter durations. This like scale, that's where the efficiency makes.
So we'll kind of slide in to the next presenter, who's Colin Riley. Rob, thank you so much for that presentation. And then for any participants, I just wanted to remind folks, please write down your questions, throw them into the chat. We are monitoring it, and we'll have some time at the end for Q&A, and hopefully Rob will be on. I also have to apologize to everybody. I missed an opportunity. It's challenging being a presenter at the beginning when Jeremy was asking me about my last name. Jeremy, je suis Québécois, so it can be called Messier. But I had a question for you, sir. What is a Canadian's favorite type of battery? And it's okay if you don't have time to hop on. It is the AAA. Jeremy, it's a AAA. So without further ado, I wanted to bring on Colin Riley. He is the Vice President of Application Engineering for Rondo Energy. Colin is Rondo is an energy storage company, rapidly decarbonizing energy-intensive industries with affordable, continuous power. Colin works with industrial customers to craft high-value thermal energy storage solutions and drive deployment of Rondo technology. Prior to joining Rondo, Colin worked in GE's power generating division, where projects he championed provide gigawatts of electricity to global customers today. He's got an MBA from Clarkson, an MS in mechanical engineering from the Georgia Institute of Technology. And something that, Colin, we both share is that we both have BS degrees from Cornell University. So without further ado, I'll transition it over to Colin Riley, and we look forward to your presentation, Colin.
Thank you, Dave. And my man, it's great to learn that there's another fellow alum here. So good to learn. Well, then, good morning. It's a pleasure to be here. I'm sorry, 1 second. I just got a thing here. It's a pleasure to be here, and I really appreciate this opportunity to chat about the value proposition that electrified thermal energy storage can provide in addressing storage needs in Alaska and in industry more generally. you'll probably see the thermal energy storage technologies certainly rhyme, but I'm hoping that my perspective at Rondo is bringing a bit of a different flavor than Rob's presentation, and it just shows our approach to this relatively broad category. I'm going to do my best to hit some highlights relatively quickly and leave plenty of room for some discussion and questions here at the end. So I'm sure that many of us appreciate that replacing business as usual fossil fuel consumption isn't going to be handled by a single silver bullet solution, particularly because the specific needs of fuel consumers can vary so drastically. So industrial heat and electricity in particular represents about 36% of today's energy use. And as we see pressures increasing to decarbonize, there's going to be huge opportunities that are available to solutions in the industrial space, which are offsetting fuel use economically. Because renewable energy has really become one of the cheapest sources of energy in history, electrified heat can represent a very attractive and near-term alternative to those conventional fuel combustion usages in industry. And that can be in the form of heat pumps, electrode boilers, or as we're focused on with Rondo and what I'm going to be focusing on here today, electrified thermal energy storage. So at its core, thermal energy storage is directly tackling the biggest challenge of decarbonizing heat through wind and solar electricity. How are you most effectively taking an intermittent energy resource and making that dispatchable and continuous for the user? And as we look into integrating into industry, that's also going to impose some additional requirements that we've been focused on for effective solutions, including a real extreme focus on safety risk mitigation within these different facilities so that we're not increasing that overall risk profile. The ability to deliver heat at sufficiently high temperatures to meet process needs. We're talking things like cement and steel that are operating at very high temperatures. And you also need a solution that's going to be durable and allow you to operate continuously and on a daily cycling basis with minimal planned downtime for maintenance. These customers are looking for 8,500 hours a year of operation. So to provide an example of how thermal energy storage can meet these needs, I'm going to talk about what I know best, which is walking through the approach that Rondo is taking with our heat battery solutions. And we're converting that intermittent electricity supply into continuous dispatchable heat directly on industrial sites through a product that's a drop-in replacement for boilers and furnaces. So Rondo's storage medium that we use is a superheated refractory brick material. And this is a material that's been used for thermal energy storage purposes in the steel industry for centuries in caliper stoves. And we're converting electricity to heat through resistive electric heaters. So I'll take a couple moments and just show you how electrified thermal energy storage works in a heat battery, in a Rondo heat battery. We start with an intermittent alternating current electricity source at a medium voltage. And that electricity can be coming from direct renewable, off-grid renewable generation. It can be coming through a grid interconnect, or it can be even from a common bus bar of those two different sources together at the facility. And so that's provided directly to the heat battery solution. Through a system of radiant heaters, the brick material is quickly and uniformly heated up to a storage temperature of over 1,000 degrees Celsius. We can charge very rapidly, getting a full day's worth of storage in as little as 6 hours, 4 to 6 hours. So to deliver that stored heat, we blow air at atmospheric pressure through the stack of bricks. So it comes in cold at the bottom, comes out hot at the top. The temperature is controlled through multiple bypass channels, and a flow rate can be controlled through the blower itself. That air can then be used in kind of a conventional heat recovery steam generator or hot water heater, heat transfer fluid heater to deliver industrial heat at the targeted process conditions. And that can be for industrial uses and for power generation. Because we're able to customize that heat delivery directly, you're able to really flange into existing systems without really upsetting anything else within the facility. Then the heat battery can also deliver heat directly as superheated air in kind of more of an open cycle solution for integration into things such as calciners or something like that. Because we're using one form of heat transfer to charge, radiation, and another to discharge, convection, the Rondo solution can charge intermittently and deliver heat continuously through these two independent systems. And because we've got a strong insulation design, the round-trip efficiency that we see from electricity to heat conversion is actually above 98%. So thermal energy storage is good at accomplishing its core mission, which is delivering continuous renewable heat very effectively. So the conversion losses are going to be minimal, so that means that less land is going to be required for renewable generation sources to power the system. And thermal energy storage is frequently using really cheap materials with mature and established supply chains, which results in a uniquely low capital cost investment required for this storage technology. One additional benefit that you see with thermal energy storage solutions is that it's a technology that can be deployed cheaply and at scale today. Rondo's first unit, integrated into an industrial site, a 2 megawatt-hour storage unit, went online for the first time in December of last year, and we have our first full-scale unit of about 120 megawatt-hours of thermal storage that's in construction right now. Because of the versatility, thermal energy storage solutions are an attractive fit for a large array of different industries. This is from the high temperature, hard to decarbonize industries that you can read about, like cement and steel, all the way to food and beverage manufacturers. And it's really because of the versatility and flexibility of how heat can be delivered, and that we're able to address so many different industries. And frankly, on the application engineering side, often the challenges is figuring out where to start amongst this array of different places. As we zoom out from the application on a specific industrial site, we can start looking at the implications for the overall utility, to utilities. And grid-connected thermal energy storage can be an attractive technology for electric utility partners. By connecting a thermal energy storage system to the network, you're adding a large, highly flexible and interruptible load to the system, which can avoid an increase in peak loads. And as renewable energy sources are increasing the variability of electrical generation on the system, thermal energy storage can be a potential win-win solution that's sitting on the customer side of the fence. So you're providing industry with cheap carbon-free heat, and you're also enabling a deeper penetration of renewables within a utility service area. A distinguishing feature of electrified thermal energy storage systems is the ability to dramatically increase the dispatchable load on a utility system, in which a utility is determining when that industrial thermal energy storage system is charging. This is similar to the conventional idea of demand response, but dispatchable load is more like a complement to those programs. Demand response is going to incentivize curtailment when demand is high, so you're lowering your peak loads on the system. But dispatchable thermal energy storage load is incentivizing consuming when the demand is low. So when you're using those together, you have two tools that are resulting in a flatter, more manageable load profile on your system. So to pivot for a quick moment, I'll close with a brief mention of another utility value proposition that's a bit of a different flavor for electrified thermal energy storage, maybe a little bit more similar to the Westinghouse solution that we just were talking about, and that's steam power plant retrofits. Because the thermal energy storage design that Rondo is pursuing and other thermal energy storage technologies are pursuing has flexibility with respect to the heat delivery, we can design boilers that directly match the steam conditions of essentially any steam power gen cycle. And so by charging with excess electricity on the system and then delivering steam to existing steam turbines in periods of higher demand, thermal energy storage becomes electricity to electricity storage as well. And those round-trip efficiencies on these retrofits are going to be limited to the physics of a Rankine cycle. Everybody always likes to look at the round-trip efficiency. But the advantage here is that you're directly utilizing a fully amortized and mature and installed generating asset. And an additional benefit that you see is that you can actually phase in energy storage with with any sort of modular thermal energy storage design. So you can actually start by putting in a small amount and doing some co-firing with some existing capacity, and then having incremental offsets that are in line with fossil fuel retirement plans for different assets burning fossil fuels today. So that's it. I just wanted to thank you for your attention here. I hope it was informative and helpful, and I'm looking forward to answering any questions that you have.
Sounds good. Thanks so much, Colin. And Rob, if you want to turn your camera on, hopefully it'll work okay, and hop on the screen here. We can do some questions that have appeared in the chat. And folks who have questions but haven't typed them in the chat, now is the perfect time to do so. So we can get some more information out of these great presenters. And so I'll start off with one for Robert. Rob, can you comment a little bit on the electrical kind of round trip efficiency of the Westinghouse long duration energy storage from I guess in comparison specifically to some of the other technologies, electrochemical storage technologies that we've heard about today?
Yeah, the round trip efficiency, electricity in, electricity out, total round trip is going to vary depending on. You've got leverage you can pull in the design from a cost perspective, but generally at 100 megawatts, you're looking at 60 to 65% total RTE.
Awesome. Thanks, Rob. And then Colin, can you elaborate on your comment a little bit? I know it was on the slide, but and I'm knowing that Rondo's predominant kind of use case is probably for thermal storage, but the round trip efficiency when it's used for electrical storage.
Yeah. So the value proposition for the Rondo's technology in electricity to electricity storage is really focused more on the utilization of existing assets. And so if you think of coal plants that you might be retrofitting today, the round trip efficiency or the fuel efficiency is going to be on the order of 35 to 40%. We're still going to be within that thermodynamic cycle, but in a lot of ways we're actually slightly more efficient than that because you're going from a maybe 80% efficient boiler to a 98% efficient Rondo thermal energy storage system. So you do see a slight increase in that nameplate efficiency, but we recognize that the real value you're going after here is minimal capital investment and simplicity of integration into existing systems and utilizing zero cost or low value energy and time shifting that effectively.
Awesome. Thanks, Colin. And I guess a question for either presenter. One of the things that popped up in the chat was the ability to pair these technologies with geothermal heat. And so any comment there? Is that something that either of your companies have looked at?
Yeah, I'll start and talk maybe a little bit more generally about integrating Rondo's thermal storage in with other forms of heat, like waste heat or something like that. Our solution is specifically an electrified thermal energy storage solution, which is taking an electrical supply and putting it into the brick. There are other forms of thermal energy storage out there that are using some sort of heat source, so you can take like waste heat recovery or something like that and put it into a medium. There are certainly some similarities in the ways of like structuring it and the materials that are being used. So it's not necessarily consistent with what we've got at Rondo, but there are solutions out there that allow you to take some other form of heat and store it in the medium directly. Our integration for that would be a little bit more like utilizing that to maybe do some feed water heating or some sort of like more complicated process heat integration to make the most of those sorts of waste sources.
Great.
Yeah, Dave, I can add on to that just from the standpoint of, I mentioned that we've got integration with the storage and nuclear power plants. We're definitely looking at all those use cases. It's very viable. We can take most heat sources through a heat exchanger and store the heat directly into the concrete modules. It's just a matter of designing the system for the specific fit. We have not done that design for geothermal just because it hasn't been the request yet, but it's certainly feasible.
Awesome. Thanks, Rob. And then to kind of tie into that, one of the other questions in the chat was just kind of the duration, I guess, of storage. These are obviously long duration energy storage companies. And so one of the questions was around kind of seasonal load shifting. So is it possible with either Rondo or Westinghouse's technology to, say, charge something up in summer or fall months and then discharge it in winter or spring months?
Yeah, I mean, for us, you could do it because our system will sit there and lose a minimal amount of heat, but that's not the right use case for our technology. There's other things that are better suited to that seasonal shifting than what we're talking about.
Yeah, and I think that the short answer is that we're kind of in the same boat with Rondeau. I often like to joke that long duration energy storage refers to anything greater than 4 hours, which means you're covering everything from 5 hours to seasonal shifting. And where we actually find we're fitting is in that, let's say, 18 to 36 hour window is what our product is designed to do best. So if you have daily cycles of taking an intermittent source and trying to turn that into a continuous process, that's where we're really going to shine, versus similar to what Rob was saying, storing something for a long period of time, you're just going to slowly lose it over time.
Sounds good. All right. And then Bill over on the chat had given me some flack. And so he wanted me to change up my question to you guys about geothermal and kind of ask his question specifically. So in regards to technologies, how can we plan for the profitable commercialization of deep, hot, dry rock geothermal, DHDRG energy, generally ubiquitous on Earth, where an energy storage is free? Leave the heat in the deep Earth until needed. Will proliferation of DHDRG obviate the need for new transmission and storage assets?
Yeah, that's a good comment. I'm not the right expert, but what I could tell you is we do have a couple of our engineers in the smart team on Westinghouse that have been approached and have been looking at those types of technologies with solutions, not technologies, with our partners, because that is a topic that's going to become, I think, more and more prevalent.
Yeah, and I'll say that similarly, I'm by no means an expert on the topic, so I won't opine too much around really geothermal in general. But I'll say that our solution is specifically looking at kind of a point replacement for boilers and furnaces, in which we're kind of integrating in as a unit asset for different facilities. And then finding a way to take excess electricity for that. So it's maybe a little bit more of a different use case than you would see for many of the different applications for geothermal out there.
Thanks, Colin. Thanks, Rob. Another question from the chat, kind of, can you guys comment, I guess for both technologies, Rondeau and Westinghouse, how this long duration energy storage is able to kind of be coupled with some of the, some of the potential projects that maybe railbelt utilities are looking at, specifically large wind and solar. How might those kind of be fits with either the Westinghouse or Rondeau technologies?
I'm happy to go first on this one, and I'll say that I think we're a great fit for those types of solutions. We're really looking to specifically address that idea of intermittency and level loading, and we integrate well with the spikiness of wind because we can charge very quickly and responsively, and that's one of the big challenges with wind. So we actually think it's a great fit. Anytime that you can use heat and have some sort of intermittent electrical source there, I think that we definitely have a good value proposition to make.
Yeah, I'll add on to that. So for Alaska specifically, we've been excited about it for a couple of reasons. And one is our technology not only can perform in the climate, but actually performance is enhanced by the cold temperatures and actually allows some interesting options on the cold reservoir side of that pumped thermal energy equation, where you can even simplify some things a little bit. But in terms of what the railbelt's trying to do, I mean, you look at a couple of things. So resiliency and adding renewables you mentioned, much as Colin said, it certainly, you can design the system to match, let's say, the size of wind installation you're looking for to provide an optimum levelizing of that wind. From a charging duration, overall duration, you can match it to what you're looking to do with wind. And then you can tailor the system to make sure that, because you're agnostic from the energy source, it doesn't need to only come from wind, right? It could be coming from the coal plant that's still operating, could be coming from gas. We're energy agnostic to levelize things, to then cut out your high cost generation sources, to cut out the really expensive peaking needs, the times when you have emergencies and you're losing power, add that resiliency. And, one thing we feel pretty strongly about, when we discuss with utilities or regions or the state of Alaska, it's not a one technology solves all the problems, right? But if you look at it from a broader perspective and you say, I want to add X amount of wind, I want to add some storage, I want to do this and this, I want to eliminate these assets. You look at the whole picture And then you start to figure out, what does that equation look like? Which pieces fit in? How do they fit in together? And we've seen Alaska's a unique use case. It's certainly different than what we're doing in Arizona, than what we're doing overseas. To me, it's compelling. It's interesting. And I think, as we've heard the last couple of days, there's probably going to be a few different interesting use cases for different technologies in Alaska that are going to secure the rail belt and drive generation costs down over time.
Hey, Dave, if it's all right, I would like to just, I'm seeing the questions coming in there, and I saw Mark's question there, and I just wanted to clarify that, in fact, a heat load for a thing like a mine is actually something that our technology can serve very well, because we can deliver hot air as one of the options that we've got on there, and we also can, of course, provide steam to some sort of like steam radiator for process heater and that sort of thing. So just because it was specifically raised up there in the chat, I wanted to say that is actually a load that we could support very well with our technology. So just so you know.
Awesome. Thanks, Colin. And I'll add a little bit to that, because I've heard some of the folks over Northern Star from Pogo kind of comment, and that's one of their largest energy drivers as they seek to try to bring down their carbon footprint, is just the heating up of air so they can recirculate it in their mine to bring fresh air into their miners. So the propane they use right now is one of the largest sources of energy in that scenario, that mine in Alaska, which is a fairly large mine, and it's just used to make heat. So I think it is a pertinent question, and I appreciate you elaborating on that. Rob, one other question. Do you know what the electrolyte used in the iPhone battery is? It's okay. It's apple juice, Rob. It's apple juice.
Oh.
That's
I wasn't sure. I was making sure you were asking me. That's a good one there.
Got to sneak it in, man. Another question from the chat. Hydrogen was mentioned as a use case. How does thermal storage and hydrogen work together for either of these technologies that we're talking about?
I'm not sure they go together all that well, to be honest with you. Hydrogen's an interesting equation, and you've got all these different value streams for hydrogen that, if they're working together in concert and storage can be a part of that hydrogen use, then you can have a compelling equation. Storage with, hydrogen for the sake of storage by itself, it depends on the use case, like a lot of these, but thermal storage tied in with the hydrogen, there may be some specific application that's not coming to my mind, but to me, they're a bit separate.
Sounds good. And Colin, I'm actually going to ask you a different question so we stay on track, because I get to take some moderators' preference here. I was reading through the Rondo website, and you guys are doing heat as a service, basically, which I think is something that a lot of utilities have been really interested in. Can you kind of make any comments? I know you're probably not on the finance aspect of things, but any comments on the applicability of using, whether it's through Rondo or just that kind of business model, that heat or energy as a service? Is that transferable to other technologies? Is that something else that Rondo is looking at, et cetera?
Yeah, absolutely. We found that the heat as a service model is a particularly valuable approach to take for a admittedly new technology like ours, because it is a way to bring the investment risk into into kind of a specific contract structure that basically just looks like an operating cost associated with the end user. And there's a few different embodiments of that we can certainly get creative in, and I can't do it justice here in the quick answer. But there's models in which you have a third party developer that kind of owns and operates a heat as a service provider, maybe installs solar panels or wind turbines themselves, and then just kind of sells the heat off to the end user. There's models in which the utility themselves can be the heat as a service provider and look at the heat battery as a capital investment on their end and add to their rate base. These are models that we've explored as well. It's a great way to explore the creativity of how we deploy this most effectively and meet the specific financial goals and needs of all of the different heat users out there, because every single user is different.
Awesome. Well, and we'll wrap that up. I really appreciate Rob and Colin, you guys, for making the time to present, and I'll hand things back over to you, Jeremy. Thanks so much for giving us the time.
Thanks so much, Dave and Rob and Colin. And that was fascinating. Definitely thermal. Anything is really interesting in Fairbanks. And I realized I dropped the pun challenge without actually having a good pun myself, so shame on me. But I'll come up with one. Next, I'd like to introduce the hydrogen panel. So I'd like to bring up Aaron Whitney online. Dr. Aaron Whitney is the director of the Arctic Energy Office for the U.S. Department of Energy, where she partners with diverse Arctic stakeholders to meet the energy, science, and national security needs of the United States and its allies. Prior to this assignment, she was a faculty member at the Alaska Center for Energy and Power at the University of Alaska Fairbanks, and a research scientist at the National Renewable Energy Laboratory. She grew up in Anchorage, Alaska, and earned a bachelor's degree in chemistry from Williams College in Massachusetts and a PhD in physical chemistry from the University of Colorado at Boulder. And Erin plays a key role in Alaska in analyzing the hydrogen opportunities and potential here. And she leads the hydrogen working group. And while at ACEP, as a colleague, she led our hydrogen research before taking her current position with DOE. So it is an honor to have you with us, Erin, and the floor is all yours.
Thank you, Jeremy. It's great to be here. Really enjoyed that discussion before ours. And I think that one of those questions about combining thermal storage with hydrogen storage is a great segue into our session now, which is about hydrogen energy storage. So I'm really excited to kick off this panel. And of course, I have to start with a joke. Two hydrogen atoms walk into a bar, and one's a little absent-minded. He fumbles around in his pocket and he says, I think I lost an electron. And the other hydrogen atom says, no way, really? And the other says, I'm serious, I'm positive. There you go, dun-dun-dun-dum. All right, so we are kicking off our hydrogen energy storage panel. We have two speakers today, Justin Freeman and Laurent Nassif. We're going to have Justin go first, and I'll introduce each one separately. Justin spearheads Kaufman Engineers' National Hydrogen Market Strategy, capabilities, development, and management of projects. He has a very diverse background and has been involved in hydrogen studies, Department of Energy hydrogen hubs, thank you, managing international giga projects and leading process transformations. He has an intimate understanding of the energy market and applications of various hydrogen solutions to cost effectively decarbonize market sectors. And as an advisor to client leadership, Justin provides strategic direction and strategy development to firms as they navigate the energy transition landscape. He helps businesses understand the levers they can pull to activate their strategies and turn objectives into concrete projects with high return outcomes. So with that introduction, I am going to turn it over to Justin to talk about hydrogen energy storage and some of the potential opportunities and applications in Alaska. Justin, please take it away.
Thank you, Aaron. And I thought we had gone with a slightly shorter intro. I'll work on that next time, but thanks for the elaborate introduction there. And I'm going to try to get to rapid fire. I've got quite a bit of material. I think we confused conferences here, so I had a little bit more than probably warranted for 15 minutes. But, you know, what I tend to start out with is, you know, just building on that last conversation about energy storage. There's so many different toolkits that we need to explore as we try to cost effectively decarbonize our economy. And, you know, I'm going to be talking about hydrogen today, but, you know, I always say, you know, I'm agnostic about what that technology is. It's really just what is the most cost effective, and that we pair the use cases with the right technology to, you know, commercially and cost effectively decarbonize our economy. And I do tend to like to use MAC curves a little bit to show sort of a systematic way in which you can address that via either a country level, business level, or an area level to try to understand what that opportunity is. But one of the questions I get sometimes is, why don't we just let the market work? And I think one of the fundamental things is that what we're missing is a carbon tax or some type of carbon pricing mechanism to give businesses the surety and to also account for the greenhouse gas effect. And so what you see in the global landscape is there's not a coherent pricing mechanism around carbon, and hence fossil fuels have, you know, underpinned a huge amount of our economic growth. But this is going to be really hard. And what you see the Europeans doing is the cross-border carbon tax adjustment so that you don't get carbon leakage, right? Because if you put a carbon tax in the United States, you could just get, you know, offshoring of our industrial base. And we don't want that, right? So there's a lot of government money that is coming into the space with carbon tax credits. But really, there's this question about whose emissions are they, right? So if you're not familiar with kind of scope 1, 2, 3 emissions, they're really about, kind of the primary emitter, but your secondary emissions, say you're a company that's buying electricity from the grid, those scope 2 emissions that maybe are coming from a power plant are still yours, but they're just referred to as scope 2. And then you also can have this scope 3 emissions that are even further upstream. But I'm seeing this trend where people are really focused on their scope 1 emissions. And so this use case of hydrogen, for instance, as decarbonization, but they're buying hydrogen that is gray or is being used steam methane reforming, where you're still having the CO2 emissions. So you haven't deleted the emissions. You actually maybe increased the overall emissions in the energy system, but you're able to claim that your scope 1 emissions have gone away. Now, customers don't care about the carbon intensity maybe today, some do, but what they will care about is the security supply today and the carbon intensity tomorrow. So, is hydrogen a good use case? And it really can almost factor into any sector of the economy. But, what is the technology that is there today? Like, what is the incumbent, if you will? And is hydrogen a good application? Is the customer going to choose it? So I'm going to explore some of that today in the presentation material and talk about the use cases of hydrogen and where I think it could play a good role in this decarbonization toolkit. But the existing market today, there's about 110 million tons of global hydrogen that's dominated really by gray hydrogen. So, it's fossil fuels that are really providing the feedstock to make that hydrogen. But this is the market that we have today. So there's opportunity to displace that with lower carbon intensity hydrogen. But it's mostly in ammonia, methanol, and then a lot of the refinery process where they're breaking apart those long chain hydrocarbon to make more diesel and jet fuel as part of that industrial refinery process. So this is projected to grow. There's so many different projections as to what this growth curve is going to be. It's even hard to say, but quite significantly over the next decade here. And I thought that the DOE, Aaron, that did a fantastic job of really sort of doing this national hydrogen strategy report. And one of the graphics that I highlight here is just the different opinion from all these really smart people about how much hydrogen is going to penetrate in these market sectors. So, transportation, for instance, the low end of the curve is, 15-ish% and the high end is 50%. And so, these are all estimates. These are all really informed guesses. But whatever way you look at this, it's an absolute huge market for hydrogen as the world currently consumes a lot of energy, and there's a lot of people that still live in energy poverty. So I think that, the decision criteria as I think about it is, what is the natural resources of that country or that specific area? What are the logistics to get that hydrogen to market? What is the cost? Security of supply and jobs are going to factor into, national decisions around this. But I think it's going to be an enormous opportunity over the coming decade. And some of that opportunity is going to come in the form of these DOE hydrogen hubs. So, there's some publicly available information. Hopefully the hubs will hear some information back about the 33 that submitted applications as to which ones will be doing the interviews and moving forward. But, this has really been a catalyst to really kick off a lot of studies, a lot of efforts, a lot of projects. As they're competing for this hydrogen hubs. And there's projects that are commercial and are positive economics that regardless of the grant money. And so it's really sort of energized with the new tax code of 45V. There's a lot of development that's going on in this space, and I'm really excited. And I think that the U.S. is kind of a reflection of that different geography, different natural resources, renewable energy versus, geological storage for CCUS. So I think you're going to see a mixture of different hydrogen colors that come out, and that's good. But, what is a hub? So I think about hubs as sort of, you have an anchor tenant, you have this master planning, because there's so many different use cases that we were kind of talking about that, there's really sort of synergies that can be built out, but you have players and entities and industries that maybe don't necessarily collaborate to that level of detail. And I think the hubs help enable that collaboration across industry and across sectors. So that shared infrastructure and that mutual benefit helps to lower the overall cost point of that hub. So, a hub can have various different ways in which there's power, which there's energy, with their storage, the production method of the hydrogen, how you transport that. I think a key enabler with a lot of this is in the beginning, particularly, trying to, as much as possible, minimize that logistics infrastructure so that you're producing the hydrogen as close to the use case as possible so that you're decreasing that logistics cost. But there's a lot of emerging, interesting use cases around there. And, we're going to kind of go into those in a little bit more detail. Home heating, we have this amazing natural gas infrastructure in the United States. And generally, the study has kind of shown that, you can increase the blend of hydrogen. Hawaii does this to about 20%. And there's a number of DOE studies that, with hydrogen embrittlement and other things that can happen with hydrogen in lines that maybe are not designed for it. You got to be very conscious about that. But generally, it's kind of, 20%. And so that's a big number in itself. But I think we have to come at it also from a cost point. As you think about, the moonshot for hydrogen is $1 a kilogram. Well, that translates to about, $8 for equivalent natural gas price versus kind of the higher end of what you see some hydrogen being sold for in market today could translate to $135. So, I think we need the cost to come down for hydrogen for it to be more readily adopted. And light duty transport, that's already a use case today. But when people buy hydrogen cars, that they get a fueling card, it might have $15,000 loaded on that card. But what you see there is a map in the Los Angeles area, about the hydrogen stations and do they have hydrogen? Is there supply available? There's a big gap in the middle of Los Angeles where there's no fueling stations. So, it's a little chicken and egg. But from a customer acceptance, do people feel safe? Just as a mechanical engineer by background, I see this, high pressure tank that's sitting underneath me in the driver's seat. And it makes me a little bit nervous, but I'm sure there's excellent engineers at the automotive industries. But, thinking about, buses as light duty transport, I'm a little less bullish on that, but I think buses is definitely a great use case for hydrogen. And this is some information from Ballard where, you're seeing these buses, they're basically electric buses, but instead of the big battery packs, you have the hydrogen as the fuel source, as the energy storage. And they have solid performance with winter is a major issue with some buses that we're seeing with the electric, where they're really decreasing their performance through the colder months. So I think, buses is really going to be a great use case for hydrogen. And then as we were talking about hydrogen earlier with the power industry, I performed a speaking engagement with a whole bunch of OEMs, and their message to me was, Justin, technology is not the barrier. They said cheap hydrogen is, because we're having units that are going to be able to burn 100% hydrogen. There's units that can burn hydrogen today. And then you also have fuel cells as an alternative peaker power. So, fuel cells are using hydrogen today in forklifts and other applications. But peaker power maybe as a different model, and hydrogen being that long duration energy storage. Aviation is another emerging use case for hydrogen with sustainable fuels. You've got synthetic jet fuel that's very costly, and hydrogen could be that form of high energy per weight. It's not high energy per volume. So, that's the one rub, is that you do have to compress that hydrogen so that you can basically get it to the place where you have the volume. I like to joke that my professional opinion or goal for my kids is that, I'm going to put some hydrogen on those rockets going to Mars. But that's already a use case today that we see. So these hubs have really help two ways, and it helps accelerate the free cash flow, that break-even cost. And so what you see there is, projects that would maybe not be viable today with the DOE cost share and with the 45Q or 45V tax credits. You have a pathway for large-scale hydrogen development that otherwise, may be difficult to make happen. And that 2 points there. You're decreasing the capital requirement, and you're also accelerating the cash flow with the break even. So, and really, when we've done studies around what really makes the economics move. Now, this was done for green hydrogen development, and this is just sort of a generic one. Is that you really need that offtake agreement. You're seeing an announcement just today with the Saudis that they basically put on hold some of their hydrogen development because they can't get firm offtake. So you need offtake agreements so that you have the surety of a customer, and then you also need that surety around what the capital costs are going to be, your operating costs. But price is definitely the biggest needle mover that really drives the economics, and then some of the other things become decreasing less importance. So, I'm a big believer that, repeatable hydrogen facilities and designs are going to be one of the ways to drive the cost point lower. So, this is sort of a generic design of how to take, renewable energy from either solar or wind, that long duration energy storage that we were talking about. We're seeing use cases where you can overbuild, the solar, by maybe 3x, but you need to be able to then run your hydrogen electrolyzer to drive the asset utilization, and you don't necessarily want to draw that from the grid. So to me, I think there is a use case where you're pairing renewables, you're pairing long duration energy storage with electrolyzers to make hydrogen so that you're getting the highest asset utilization of your electrolyzers without having to draw that electricity from the grid. So I think there is a potential mixture of technologies there that would then help eliminate the grid infrastructure and really kind of create your own microisland. And that's all, around, can you get those repeatable designs at scale? Design once, build many. That really helps drive the project management, drives the engineering costs out. You get your workflows, you get your processes, and you can really, kind of take a factory approach to drive efficiency and scale your business. So for Alaska, a large part of electricity grid is still supplied with hydrocarbons. I know there's a lot of activity going on with the laws and regulations that are happening in Alaska right now, but it's a big component of our grid, and the rail belt is hydrocarbon based without the surety of some of the natural gas supply here in the next decade. And then we emit, not a lot of emissions in the state. I mean, we're a couple of different refineries sort of worth, if you will, but we export a lot of emissions via our oil exports. And, the North Slope has an enormous resource base still of roughly, depending on which study you look at, 9 trillion cubic feet of natural gas. And so we're a resource rich state. And, but I think, hydrogen or the various forms of hydrogen carriers are a great way for us to export the energy and keep some of the waste product of CO2 to have some beneficial use for enhanced oil recovery in the state of Alaska. And another big thing too is, and this is common through all of the grids, as you have more electrification, as you have more heat pumps, a lot of things that were maybe, emissions in your burner or your stovetop are going to transition to the power grid. So you can kind of think about, some of that power grid, although Alaska has kind of been decreasing every year, you could see with, battery, with people buying battery cars or trucks, some of that is going to come, that load is going to be transferred from this thermal load that we have today into electrons. And so I think the grid needs to prepare for an increase in demand in the state as we electrify. And Alaska's got fantastic geology. It's got all of these things. So as we think about blue hydrogen, as we think about the ability to, do hydrogen in various pathways, we have all of the ingredients. We've got saline aquifers, EOR, depleted oil and gas, basalt. So we've got all the ingredients to be able to do that. And I just think this is kind of a funny one. Alaska, it is half dark half the year, but, Germany as a resource, the German government's put a ton of money into solar. They've got 70 gigawatts of solar installed today, and they're planning to get to 215 gigawatts by 2030. So I think there is an opportunity for solar and hydrogen to be part of the energy solution in Alaska. And the offshore wind potential of Alaska is just phenomenal. There's some statistics there on the screen that, it's a huge potential. And, think about that as a new opportunity for Alaska to, export energy to other nations or to even help with our own grid decarbonization. So, basically, the simple message is Alaska is blessed with so many different things for us to develop hydrogen, lots of different pathways, lots of different resources. And, we can convert that into export potential or as part of, security for the grids, for the villages as a way to decarbonize and improve our overall electrical system. With that, Erin, hopefully
Thank
stay
you.
15 minutes.
Yeah, thank you, Justin. I'm just going to ask one question before we move on to our next talk, and I will save some of these other questions I see in the chat for after both talks. You've given a lot of possibilities for Alaska. What do you see as the first maybe piece of a hydrogen ecosystem to move in Alaska, either piece or sector, out of sort of all these ranges of possibilities?
Yeah, I think that, when I look at renewables, using the renewable energy for the grid, it makes a lot more sense before we start to try to do anything else with it, right? Like trying to convert it into hydrogen, you've got some just inefficiencies and loss there. And so, I think that it's trying to understand what would be a good use case, and generally forklifts and sort of logistics infrastructure, hydrogen buses. So if you can get the transit authority or, some type of government involvement there where, you're getting that offtake agreement really sort of lined up where you have that surety of the use case. To me, hydrogen buses in Alaska makes probably the most sense as a starting place.
Okay, great. Thank you. I appreciate that. And I lied. I'm going to ask you one more question. And this is from Bill Leahy in the chat. How important do you think gaseous hydrogen pipelines will be for gathering, transmission, storage, and distribution in Alaska and elsewhere? How can we do it safely? How can we do it profitably? How can we repurpose natural gas pipelines? Can you speak to that at all?
Yeah, I think that one of the approaches that I really like is people using tube trailers for the last mile. And so that's where if you can really sort of co-locate your production of your hydrogen with a close proximity to your use case, then you eliminate a lot of the pipeline infrastructure, and that allows you to get out of the gate a little faster. The existing pipelines in the, US, they weren't built for hydrogen, right? And so you really have to do a risk assessment to make sure as you're doing the blending that you can do it safely. The hydrogen embrittlement is a real thing. And so there's probably going to be new pipelines that are going to need to be built for hydrogen. But that type of capital investment would really need to probably see a larger scale application in order to justify that. So unless you're just talking about 1 or 2 miles where you're just trying to kind of move some smaller scale hydrogen around, I think the pipelines would be a ways out for Alaska.
Okay. Thank you very much. All right. We are going to move on to our next presenter. Laurent Nassif is the CEO of Renewable Solutions, a company that aims at providing sustainable energy solutions via advisory, research, projects, assets, and trade. He has led a variety of renewable energy projects from new business identification to operation, and advises multiple energy and sustainability organizations. He has a PhD in engineering from Georgia Institute of Technology and executive MBA from the Kellogg School of Management. And he is a senior portfolio manager assessor for the International Project Management Association. And he comes to us from Oahu. So, Laurent, please enthrall us with some of your perspectives on hydrogen energy storage.
Thank you for the introduction. And okay, so today I'd like to talk about hydrogen storage and also hydrogen as a storage solution. And the first thing I want to touch upon is that sustainability drives the transition to the energy field. And sustainability means three different things. First, it's fighting the global climate crisis that we have, which is both urgent and important. And typically, the way we look at it is by reducing greenhouse gas emissions. There is other ways, obviously, of addressing that. The second pillar of sustainability is sustainable development, which typically means increasing the use of renewable resources into our processes. And the graph that is at the bottom of my slide here comes from the EIA and show that there's going to be an increased demand in renewable sourced energy and firm energy. The third pillar of sustainability is protecting the environment, which we see typically as reducing pollution and reducing waste. So sustainability drives the transition. And it also drives the need for storage, both for power systems and gas systems. The curve that is on my top left is called the duck curve. Everyone, I think, is familiar with that curve. The basic component of it is that you have first a base load, which is basically the constant demand for power you're going to have during a day. And that's typically is provided by firm power, things that you can turn on and turn off relatively quickly, and then it can produce the entire day. Everything that is above that is called variable load because, well, it varies during the day. And the part of the variable load that is the most important to look at is a peak demand, which typically occurs between 6 p.m. to 9 p.m. Basically when we have a need for light, we have a need for heating, we have a need for cooking, and in Hawaii, we have a need for tiki torches. So the peak demand occurs in the evening. And if you look at intermittent renewable energy, such as solar power, which is depicted by this triangle, your peak production occurs around noon. So the question is, how do you bridge that gap between when your peak production is and when your peak demand is? And even more than that, you never design a solar farm based on your peak production. You design it, with the safety margins, so lower than that. And then the last thing that you look at is how do you ramp up from when you produce the energy to when you need the energy. The graph on the right look at the seasonality. So this is a curve from a solar farm. And basically what it shows is that not only you need to have storage to address your need during the day, but what makes sense is that, you have more sun during the summer months than you have during the winter months. So you have big variation into the energy that you can produce during the year. And so you need to have a storage solution that also is long duration. Finally, if you look in the graph on 6, this is a screen capture that I took at the end of 2019, beginning of 2020, so right before the COVID pandemic. And what it shows is that you have basically no T&D capacity left going from the major cities and agglomeration in Oahu. And so you also have to have a storage solution that allows you to manage the load so you can transport it and distribute it as well. The last graph I took from a CID conference in October of last year, and it basically shows the discharge, which is basically a volumetric flow rate for hydroelectric purpose. And what it shows is that in the 1980s, when most of these hydro assets were put in place, we designed it with the idea that we will have a large volume discharge that will be pretty wide and just only one during the year. But with the effect of climate change, this is changing significantly to the point that now we're seeing that we're expecting that we'll have two peaks in the discharge volume during the year. The major peak will be smaller, a steeper decrease, and then you're going to have a second peak. And what that means is that we have to start thinking about, did we over-design? Did we under-design these assets? How do we change operation? What is the impact of safety? And of course, the need for storage is also for gas systems. We are looking at displacing some of the gas energy by hydrogen because of the sustainability benefit. And what I mean by that is that when you look at the greenhouse gas life cycle for any of the processes, what you find is that 80 to 85% of the greenhouse gas footprint comes from when you generate the energy. So for power, it's when you burn, coal, oil, gas, to generate the power. For gas is when the customer burned the gas to generate the heat or cooking or things like that. So hydrogen doesn't have any carbon in it. Therefore, it doesn't generate any kind of CO2 during combustion, and that's a big advantage of hydrogen. And so you're looking at displacing some of those gases with hydrogen. So let's look at the type of hydrogen storage that are available. And before I do that, I want to mention that by hydrogen, we are looking at not only H2, but we're also looking at hydrogen carriers. So that includes renewable natural gas, which is 1 carbon for 4 hydrogen. We're looking at ammonia, which is 1 N for 3 hydrogen. We're looking at things like methanol, which is 1 C, 1 O for 3 hydrogen. And we can also look at gas and also liquids. Ammonia and methanol are both liquid. So I took the slide that is at the bottom here from the US DOE, and what it is, I completed it with other things that I think are of importance. The way the DOE delineates the type of storage is that on one hand, you have material-based hydrogen storage. And what I did is that I added to the box of ammonia to include all other carriers, including in that case also methanol. The other side is a look at physical-based storage and what I call static physical-based storage. And I had it a geological storage, which we've seen, at the beginning of this workshop yesterday, where we talk about cavern, for instance, right, which is the ultimate static type of storage. And then I added to that dynamic physical storage, because you can store hydrogen also in tube chillers, which was just mentioned. You can also store it into a pipeline with dedicated pipeline or blending, which is something that Hawaii has done for more than 100 years. So very briefly going through the static physical storage, the idea is that you can use the same solutions that are applied to renewable natural gas or natural gas. You're talking about vertical tank, horizontal tank, bullet, which are basically big tanks, and a cryogenic tank or spheres. All of those different things you can use also for hydrogen. The only difference is the energy cost to use these. So if you're looking at compressed hydrogen, you want to compress it at 350 to 700 bar. It costs you typically 5 to 20% of the lower heating value of hydrogen to do that. If you're looking at liquid hydrogen, you basically need to have a phase change, and you need to have refrigeration. So it's going to cost you 30 to 40% of the lower heating value of hydrogen to do that. And you have to constantly vent the hydrogen that forms into the tank. And then you can look also at cryocompression, which basically allow you to have that phase change with lower pressure. And that's what people are very interested in ammonia, because ammonia is a liquid and you can store hydrogen, in that form relatively inexpensively. Actually, if you mix ammonia with water, you can even store it at ambient conditions. And if you look at dynamic type of storage, you can use tube chillers. This is the exact same tube chiller that you're using for renewable natural gas. The only difference is that the BTU content of hydrogen is roughly half of the one of renewable natural gas. So if you use that solution, basically you can store less hydrogen in your tube chiller, but you can still do that relatively inexpensively depending on the condition. And you can also use pipes to store hydrogen. You typically get 1 or 2 days, worth of storage in your pipes, depending obviously on the geometry and the lengths and so on and so forth. And that's why a lot of people look at blending. As I mentioned, in Hawaii, we've done hydrogen blending for more than 100 years. For nearly 60 to 70 years, it was at 50% hydrogen in the pipe. And then since 1974, so around 50 years, it's been at up to 15% hydrogen in the blend. So we definitely know that hydrogen blending works. It's because it's been done for a long time. I won't go into the detail. I'll try to pass through this slide very quickly, but what I want to highlight is, first of all, there is multiple ways of generating the hydrogen, and the 3 main ways are electrolysis, where basically you use a renewable source for power, and you use that to break down water into its elements, hydrogen and oxygen. You can use reforming, typically steam reforming, where you use an hydrocarbon, that could be naphtha, that could be a natural gas, and with water as steam, you basically break down the hydrocarbon into, hydrogen and other carbon product. You can also use gasification, which typically use a waste biomass, such as a woody biomass, to generate hydrogen blends. And then you can blend the hydrogen. You can store it, you can convert it into methanol and ammonia, you can use it for biofuel production via hydrogenation, you can convert it back to power either using fuel cell or cogen solutions such as internal combustion engine or turbines. The photo that you have on the right is actually a boat that goes across the ocean that is solar powered and wind power, obviously, and that use actually both solution, both a battery for short-term storage and hydrogen for longer-term storage when they go through long stretch of water. I think this slide is the most important slide of the entire thing that I wanted to present, is just to show that these things that I'm mentioning around hydrogen are already operating. There are operating assets that are doing that. The first one, which is at the center and then on my bottom right, is a demonstration plant that is basically using electrolysis as a way to store energy. And then in that particular case, they are blending it with natural gas. So they use solar energy, but you can use wind energy. They use electrolysis to generate the hydrogen. They store the hydrogen in a tank, and then they inject it into the natural gas pipeline. You could also reconvert it back into power. The asset that is on the top is a plant that is doing gasification. It's a modular plant that is using municipal solid waste, and they use that to generate either renewable natural gas or generate hydrogen. And in that particular case, it is linked to a Jan Bakker internal combustion engine to convert it back into power. And then the asset that is on my left at the bottom, that's the asset I was talking about since 1974 that is using, in that case, the byproduct of a refinery, which is called naphtha, and steam reforming recycled water to generate hydrogen and hydrogen natural gas blend. And that is injected into the natural gas pipeline. It's been done for 50 years with that particular plant. There is also two associated projects, one that is looking at using the hydrogen that is being produced to connect that to a fuel cell to generate power to supply to the plant. And then another one that is linked to it, which is similar to the demonstration plan that I've been talking about, which is basically using solar power to generate hydrogen, store it, and then in that case, inject it into the pipeline. I won't go through that slide. The thing that I wanted to show there is we've seen so many different solutions during this workshop, right? And they're all good solutions. So I could do the same thing and I could say, well, if you look at time, if you look at scale, and then you can derive a cost, you would see that hydrogen is 4 to 5 times cheaper than battery, and it's at par with pump storage hydro, and it's natural gas is basically 8 to 10 times cheaper, than battery, right? But what I'm trying to show is that, well, if I did that comparison, right, I'm missing a lot of elements. I'm missing question about the asset life, the response time, the efficiency, the sustainability, the availability, the safety, footprint, the capex, the opex, etc. Right? So the key point from that slide is that all of those solutions are good solutions. And they're all dependent on basically your location and your specific conditions. And one may work very well for your location and one may not work very well. So what are the key takeaways from that presentation? Well, the energy transition and sustainability drive the need for storage. Storage is needed for all renewable energy integration, but especially to enable variable energy such as wind or solar. Hydrogen is one of the main solutions that we have. It's flexible, it provides long-term, large-scale energy storage, and it uses most of what we're accustomed to use for natural gas in terms of solution and flexibility, added flexibility with carriers. It also works well with other storage solutions for specific application. We saw the boat, right, that use both battery and hydrogen for storage of energy. And there are multiple type of application and projects, which are real projects that you can see and have operated for a long time. So if I were to summarize what I learned from that workshop, I would say if your question is which storage solution is best, the answer is yes. All of the solutions are really good solutions. You just have to look at, what location and what specific conditions make sense for different type of storage solution. And that's it.
Thank you so much, Laurent. Wonderful overview there. I'm going to kick off a question here, and then we've got a bit of chatter in the chat box here. You mentioned a couple of the projects involved in blending hydrogen into natural gas in Hawaii. And I'm wondering if you can say more about how that's worked, the pressures that are used, because, there's a lot of conversation about how hydrogen blending will lead to embrittlement. So does Hawaii have special pipes? How has Hawaii managed to pull this off, and what can other places learn from the blending that Hawaii is already doing?
Yeah, so I can definitely share a lot more about that. I'm very plugged in with all the efforts related to hydrogen in pipeline, not just hydrogen blending, but also looking at coating and also looking at, new pipe, all of these different solutions. The short answer to one of the question is, does Hawaii has different type of pipes? The answer is no. Those are the exact same pipe that you would find anywhere else in North America. It's basically a mix of steel and polymer pipe. The transmission line is made of steel. The distribution is roughly half steel, half polymer. Does Y has different type of end-use equipment than anyone else? The answer is no. It's the exact same. The only thing that you may have to do is maybe a little bit of adjustment on your on the nozzle in some of the residential equipment, basically adjusting the Wobbe index, and so you have the right flame appearance for your use, like cooking and things like that. I was in charge of the cogeneration system that uses that blend as well. We didn't experience any kind of specific issues. I know a lot of people have been mentioning that when you start going beyond 20% hydrogen in the blend, you may have some knocking effect, because basically, you have to pressurize your blend, your gas, right? When it goes into your internal combustion engine. But obviously, at the level that we were looking at, we never had any kind of specific issues. And I know that the manufacturers have been looking at that, not only at 100% hydrogen cogeneration equipment, but also what kind of retrofit may be needed to increase the amount of hydrogen for this type of system. So the experience has been, obviously, we don't have any specific issues. As I mentioned, from the early 1900s all the way to 1974, it was 50% hydrogen in the T&D system. After that, it was up to 15% hydrogen in the system. Now, here is the thing where you want to be very careful about. It is very dependent on your operating conditions. And what I mean by that is all the operating condition. People talk about the SMICE, but it goes even beyond the SMICE. You want to look at things like pressure, temperature. You want to look at the material of your pipe. You want to look at the geometry of the pipe. You want to look at the roughness. You want to look at what kind of ratio of hydrogen you have, which affects the viscosity and the flow. You want to look at all different elements in your pipeline system, not just the material, but also the weakest part of your system, which are the joints. And then you want to look at any kind of operating conditions. Do you have buried pipe, which, provide insulation and a barrier, for hydrogen, to flow through? What kind of survey equipment do you have? What kind of limits does the survey equipment has for detection? Do you have monitoring, and so on and so forth? So it's a very loaded question. And I'm working with a lot of different organizations right now to kind of like provide an answer, to that question, right? But the way I would summarize it is that from an operation standpoint, what you find is that within a certain operating envelope, you have no expected impact really, on your system. You can expand that operating envelope based on the information, the operational data that you have. And then when you go beyond that, basically talking about very, very large pipes or very, very high pressure systems, then you can't really use that operational data. You have to rely on laboratory experiment to guide whether you have an issue or not. The last thing that I would add, if I can add one last thing, is that there's an operating envelope, and you want also to think about the safety aspect of it. You may decide that you can operate, at certain conditions, but still had safety equipment like monitoring, coding, another pipe, just to make sure that you have an additional safety barrier to any kind of leakage.
Okay. Thank you. There was a clarification question in the chat. Did you say it was 50% mix in the pipes before 1974? Did we hear that correctly?
50%, 50% before 1974 and 15% after 1974.
Okay. So would you have any advice for Alaska thinking about potentially blending hydrogen into its natural gas lines?
Yeah, absolutely. I think, it's a great option for Alaska because obviously I have the experience doing that, in Hawaii, and some of those hydrogen solutions, which could be more challenging in Hawaii, don't have the same type of challenges, in Alaska. So Alaska have an abundance of renewable energy sources, as Justin just showed in his presentation. There is also an abundance of water, which are the two things that you need, for electrolysis. You also have biomass and waste that could be used with gasification to produce, hydrogen. So all of those things make complete sense, to me, for Alaska. And I'm not even touching about all the other potential that Alaska has. It's just the land of abundance. You have also geothermal, you have tidal, you have wind, you even have solar. I mean, it just goes on and on and on and on.
That's great. Thank you. I just want to summarize a comment in the chat here. Looks like Mark Masteller may have made a comment that I thought was just an interesting tidbit to chew on. I think I'm understanding it correctly. He says, if rail belt utilities move toward importing LNG, could that infrastructure, i.e. ships or tanks, potentially be used to move and store hydrogen produced from, like a wind resource in the Aleutian? So I love the thinking about sort of dual use here. There's also a comment from Bill Lady about potentially using Southeast Alaska hydro plants to fuel cruise ships if they make a switch to using hydrogen, and whether that would be a realistic scenario. Let's see here.
So I can comment on the LNG infrastructure. And when I looked at that for basically CO2 and natural gas, kind of using ships for that application of kind of shipping LNG from Australia to Asia and then backhauling the CO2. Working with our shipping group, it was generally determined that we could do it from an engineering perspective, but from a logistics perspective and like shifting over from, CO2 to natural gas and just the logistics of that, it really didn't make sense. It was made more sense to just have dedicated shipping lines for the particular use. Mm-hmm. I'm just looking at the critical, pressures and temperatures of the two gases. I think they'd be quite different enough that that would be problematic. It's an interesting idea, but at least in my previous experience, it made more sense to have dedicated vessels for the product.
Okay, great. I appreciate that commentary on the spirited discussion in the chat. If there are no further questions, I am going to wrap it up here. We've already run a little bit over, but I very much appreciate the time that both of you have taken to share your expertise with us, and I'm sure there'll be lots of follow-up conversations. So thank you both, and I am going to hand the floor back to Jeremy.
Thank you, Aaron. Thank you, Laurent and Justin. Learned a lot from that. I really appreciate you sharing your experience with us. Thank you to all the attendees as well for joining us. One thing I really took away from this whole workshop is that there's just not a single silver bullet, and that you really just need to match the solution to the need. And every application is different. And so that's the kind of real challenge to take away from this. And when considering, which solution we want to try to target. And I also want to say that the other day I drove to the transfer station and I picked up a dead battery took it home. I don't know what I'm going to use it for, but it was free of charge, so I did it anyways. So there you go. But thank you all for joining us for the Energy Storage Beyond Lithium Batteries virtual workshop, sponsored by the University of Alaska Fairbanks and the Alaska Center for Energy and Power. The recording of this workshop will be available on the Alaska Sustainable Energy Conference website at www.alaskasustainableenergy.com at a later date. Please continue to check back for more information. We'll also be sending out a short survey following this workshop, and we would love to have your feedback. You can access this survey by scanning the QR code on the screen now with your camera phone, and we'll also drop it in the chat right now. As a reminder, everyone who completes this survey will be entered to win one 3-day conference ticket to the Alaska Sustainable Energy Conference this month. The winner can select either an in-person or virtual ticket. Please take a moment to get your short survey submitted to help the planning committee improve future workshops. We appreciate all the incredible moderators, presenters, and virtual attendees. So we hope to see you all at the Alaska Sustainable Energy Conference at the Denina Center in Anchorage on May 22nd and 25th. Both in-person and virtual tickets are available for the conference, and we hope you will consider joining us. In-person and virtual tickets can be purchased now at www.alaskasustainableenergy.com. Thank you.